Okay, good afternoon. Thank you for joining us today. Initially, the sessions will be in English. If someone has problems, I think that we have their equipment to allow. But I think that everyone understands English. Yes? Okay. First of all, we would like to thank Nassertic for hosting this event inside the Jornadas de Usuarios de la Red, that you know that are organized yearly. We would like to thank also to all the speakers because they are coming because they want to present their work and they are coming paying in many cases their own cost. So it's something to thank them, and I hope that they will be here in the next session because there are some people that are still missing. Well, this event is organized by Quantum Spain. In Quantum Spain project is a national initiative funded by the SCAYLE that with the idea of building an ecosystem and an infrastructure of quantum computer. This infrastructure is composed now by one quantum computer, well, in fact two, that are hosted by the Barcelona Supercomputing Center, plus other initiatives in order to create a support infrastructure. For example, now we have technicians in all the supercomputing in the Spanish supercomputing network nodes. We have a program that is TalentQ for promoting the last activities in research in the world, creating or organizing webinars, usually every 15 days, plus courses, hackathons, and some documentation about our systems with examples, with notebooks about different techniques that this TalentQ platform is open to everyone. And I hope that the platform can survive after the project. And finally, we have a set of research programs that are mainly executed by the universities around Spain in order to foster the software ecosystem that use the infrastructure that we will provide. Also, we are generating emulators, and two of them will be presented today by SCAYLE and by CESGA in order to help the software developers to develop their solutions or to test programs inside this system without the need of accessing directly to the quantum computers. That is expensive and they are scarce, you know. One important fact is that we have the first results about the open call that we did before summer. For me, the numbers are impressive because we didn't expect such a big number of proposals. In fact, if I didn't count wrongly, we had 31 accesses for the quantum computing Barcelona Supercomputing Center, 11 for our own quantum computer at CESGA, QMIO, that was integrated. It's not part of Quantum Spain project, but we had this quantum computer and we have the compromise to include in the Spanish supercomputing network offer. But 5 of them will use both systems because they need to test different things. So this means that we have around 35 research groups that have now access to these platforms. The second open call closed today, I think. Okay, I don't know if it's closed at this moment or not, but if it's not closed, you have still the opportunity to submit new proposals. And we hope that the numbers will be almost the same or better. But it's something that, you know, has a lot of steps because they have to pass the scientific evaluation, so we have to wait. Secondly, we have to say that we have a very intense day ahead because we have 3 sessions with scientific results, but plus 1 session about our own research infrastructure in Quantum Spain. So I hope that at the end of the day, we can have a better understanding of the needs of the users. So I encourage you to make questions and comments, especially in the last part of the session. So don't hesitate to ask the technicians that we are around or to comment new necessities, because these kind of comments and questions allow us to define the next infrastructure. So thank you again for coming, and we can start with the first session. But I have to make a comment. We have one of the persons that have to present the SCAYLE infrastructure. He's had some problems with the train, so he's not here. So we will delay her presentation to the last session. So we start with the first session presenting the infrastructure, the quantum infrastructure, and the first presenter is Raúl from Barcelona Supercomputing Center. Raúl.
Hi, yeah, okay, better. So my name is Raúl. I'm a technical quantum support from BSC, Barcelona Supercomputing Center, and I will present the MareNostrum-Ona, a new partition of MareNostrum, that the idea is that is connected with MareNostrum-5. This is where MareNostrum-Ona, the quantum cluster, is installed. Here we can see two different chips, two different quantum computers. On the left side is the red one, and the right is the blue. The blue is the one that is now in operation, and the left one, the red one is still in calibration stage, but we expect it to open to the users in the next weeks. But it's quantum. We never know what happens with the calibration and other problems. So here you can see the quantum computer inside the refrigerator. Here is where the chip is installed, and in the bottom of this picture is where the chip is. Here is where the millikelvins is reached, and here is an example of the blue chip that we installed 6 months ago, but we already changed this chip and it's not in production anymore. So MareNostrum-Ona, so the idea is a quantum cluster is a typical cluster, but with 2 chips connected. Here you can see that we have two logins nodes, the 1 and the 2, and from that logins you can send a job to the quantum computer that, for example, from the login 1 you can send a job to the blue, and we'll connect with QBlocks, that is the system that has the connections to the chip, and from that you can extract the results and do whatever you want in MareNostrum GPP or in the login. And with the same, you can also connect to the red, but red and blue are not never, so you cannot talk with blue and red at the same time. You can talk in the same time if you ask for the both nodes, but for now the connection is classical, not quantum. It's not quantum connection between chips, it's only classical. From the file system, GPFS, that is the file system that is also in MareNostrum-5. So everything that you do in the quantum cluster, you can do in the MareNostrum-5 cluster. This is the idea of the MareNostrum 5 partitions. Here you can see that there is GPP, ACC, and ONA, because the idea is that is one partition more from the MareNostrum 5. And also you can see in the bottom that there is next generation partitions. So at the end, we will have like 5 different partitions in the same MareNostrum cluster, with the idea of using only ONA to boost your code and not for all. And you can use CPU, GPU, or next gen, like as you can see here. What we have right now is in the Quantum Blue, you can see that it's only 5 qubits, but this is part of 20 qubits chip. So right now we have 5 qubits with this topology. That is the chip that is actually running in the Quantum Blue. And in the Quantum Red, we expected to open in the next weeks, but we had some problem with the calibration of the 2 qubit gates. So we are now checking that it's all correct again. And this is the 11 qubits topology. So the idea is both of them, Quantum Blue and Quantum Red, is part of a 20 qubit chips. So right now you only have 5 qubits open because it's the ones that we calibrated fast to give the users the option to run some code. But when the 11 qubits are open, we will close the Quantum Blue to calibrate full chip until we have 20 qubits in the Quantum Blue. And in November, the Quantum Red will start the installation of the last version of the chip, that is 35 qubits. So from now, we don't know the topology of this chip, but the idea is the same. We will try to keep always one chip open with this topology or some part of this. And until we end at the end of this year, we expect that we have already 20 qubits in the Quantum Blue and 35 qubits in the Quantum Red. Also, I want to mention that we will have another quantum chip, but this is not from Quantum Spain, from the European project, that will have 10 qubits, but will be analog one, not a quantum gates. So the idea is, if you ask for the quantum project of the Europe, you will be able to access to the Quantum Blue, Red, and also to the other one that we don't know the color, but maybe black or green. So which are the fidelities of the chip? We expect that at least for the 1 qubit gauge fidelity is above 99%. For the 2 qubit gauge fidelity is above 90%, and T-out fidelity it's above 85%. So the values will change every day after the calibration. So I cannot just show you after that I can show you the web page where we put the calibration results. But right now we don't have the automatication of putting the results of the calibration every day. So this part is not already done. But yeah. The native gates of the chip, of both chips, is the drag pulse and the control Z gate. And also you have access to the pulse level access, and you can work with all of the details of the chip. If you know how to run with pulse, you can send it. Here you can see one example of the results that we are obtaining, but this is not complete. But for the chip of 11 qubits, the red one, this is the fidelity result. And here you can see 86%. So from that, we consider that the chip is already calibrated, and we can start to go to the other qubits. So the idea is when we open the chip to the users, we expect that all the qubits are at least some part calibrated. And the typical T1 that we are obtaining with the results is 20 microseconds. How to access to the chip and send jobs and do that? The idea is that you need to have a HPC user that you obtain with the res access. And from that, you just do an SSH to the cluster. and you only need Python with Kibo and Kililab. From that, you can run all you want in the chip. And for example, you can create this circuit that is just adding a X gate and a Hadamard, and you execute to the platform that is an RAM card. And when you obtain that, you need to create the SVATch script, that is the one that works with Slurm. And at least you need to specify the account, that is where you are using the hours of the rest, and also the queues, because it's just how much time you can use the chip. By default, it's 10 minutes, but if you justify, you can ask for more. And finally, you just load the Python and execute the circuit, and you can send the job. This is the queues that are already in the cluster. The short quantum span is the queue for the quantum span project, to the idea that you have access, but it's more limited to 5 minutes. And for the rest users, you have a 10 minutes wall clock by default. But you can ask also for more if you are justifying why you need more than 10 minutes. You need to take into account that this time is not QPU or quantum time. It's all the connections that you need to do to the chip and all process that you do in the quantum cluster. So it's not that fast. So the connection to the QLOCs is taking like 20 seconds, something like that. It depends of how many qubits have the chip, because with the 5 qubits in the first version take only 10 seconds. When you connect more electronic, you are taking more time to the connection. Next steps that we expect that in the next months we can obtain all of this is connect with MareNostrum-5. This can give us the idea of running hybrid jobs with GPP or ACC and with the quantum cluster. But for now, what we do is in the quantum cluster, so I will go back to explain this part. In the Q01 and 2, the one that connects to the blue and to the red, each node is with 40 cores, so you can run the classical part in this node, but the idea is that we want to connect with MareNostrum-5 to use all the nodes of GPP that you want. Also, the idea is to obtain to the users the daily calibrations. This part is not done for now because we are waiting for the 2 qubit gates calibrations that we have some problems and we want to give the good results, but we expect that it's working in the next month maybe, we don't know, but the idea is that. Also improve the documentation. We are starting to work in the hybrid jobs, pulse level and the calibration examples to give the users a more family infrastructure to run the code. And finally, do a benchmark of what we have and give the users more idea that how much time you take to the connection, how the hybrid jobs is done, and the times between the connection to the MareNostrum-5 and to the cluster. And here I put the link to the documentation where you can see all the details, and the idea is that here you also can see the topology of the chips available and the calibration of the last day. But right now we don't have this automated, so I can show you here. This is the web page where you can go to the HPC clusters. You can go to MareNostrum-5 if you are interested. But if you go down to the quantum, to the system overview, here you will see the topology of the qubit that is in production. Right now, only QBlue is in production. And if you go to the calibration part, here we will put a table that you can download with a CCU file, or we don't know the format, but the idea is that you will be able to download the table also to see the calibration. That was the last calibration that we did in the blue chip, but I think that was 1 week ago, so it's not daily for now. And the idea is we do the same with the red, but it's under calibration. And finally, we also want to put this in the cluster to just you don't need to go to the web page if you want to use the calibration. And this is the cluster, and I will send a job to give you an idea how to run a simple job. And for example, you can see that there is 3 partitions, the red one and the blue one, but also the interactive one is not connected to any chip. It's just if you want to compile some application of you want to do some classical part that needs more than 5 minutes, because in the login one, if you are doing a compilation or you are executing a Python, after 5 minutes of CPU using, your task is killed. So you need to create the interactive queue, but well, this is not important in that part. And here you can you have the circuit, the SBatch script, and you just need to send this batch, and you will say the job is sending, and just wait for the job is running and wait until it finishes. So I won't show the results because it's not important, but yeah, that's all. If you have any question. Sí, ¿cómo lo hacemos los micros? Si tienen preguntas, que hablen fuerte, ya está. Sí. Yeah.
Thank you. We share some emails. I'm Raúl, yeah, also. But I was asking you for the VQE template like a few weeks ago. Have you ever thinking in create kind of a community? Because relying on email just in 1 person or 2 persons is not enough.
Yeah, the idea of Quantum Spain is to do just that, but I think that we need to do a meeting to coordinate all of these tasks. But the idea of the Quantum Spain is not only having a technical in each node, is to create an examples to the users and create this community that you are talking about.
Okay.
So right now, I put some examples in here, but this is created for me in.
I remember.
You asked I put one.
Actually, it's the last one that I want.
Yes. So if someone asks some example, I try to put here, but it's not the idea. Is to put in a better way.
Okay. Thank you.
I just want to comment that in the web page of Quantum Spain, you can find talent queue, and there is a lot of samples that you can work on. And then also you can look for your nearest center of the RES, and then ask for a technician of Quantum Spain.
This is the page that he's talking. But we need to adapt to the chips that we have in the RES, because the code that is here is not to the chip, so you need to pass to QLab and do some changes. So it's not the final version.
Yeah, thank you for the presentation. When both of the red and blue are available, are we going to be able to connect to both at the same time when you submit a job, so like run in parallel? Can you only go to one? How?
Yeah, we expect that you are able to connect to both at the same time, but is this more a Slurm thing that you need to just send and maybe put a dependency to the job? And yeah, if the chip is free and you can send a job, yeah, you will be able to send at the same time.
Hi, Raúl. Thank you for the presentation. So right now in the blue chip, for example, so the 1 and 2 qubit gates are supported, no? But what about the 3 qubit gate? Like, it's gonna be supported at some point, or you are like not?
I'm not sure, but this is the QLab thing, because the support of this is more from the QLab, that the Kilimanjaro, what they give us. So the idea is maybe in the future, yes, but right now, for the next months, I'm sure that no.
In the near future, no.
No, okay. Only 1 qubit and 2 qubit gates.
Okay, thanks.
So.
Questions? No? So thank you, Raúl.
Thank you.
Nice presentation. We have to twist with this one. Okay. Now, again, I will present the QEmulators infrastructure at CESGA, that is part of also the Spanish supercomputing network. This infrastructure is not connected yet to Finisterrae-3, that is our supercomputer. It's not this independent infrastructure for research in quantum computing and quantum space solutions. So it's devoted exclusively at this moment to these kind of jobs. This infrastructure is composed of 4 elements. Of course, one QPU, that is, I will present later, with 32 qubits. One cluster, parallel to run jobs in parallel, based on x86 processors. A second cluster based on IRM, for running one emulator that is QULACS. And of course, shared storage for interchanging information between all the clusters. Of course, we have also the storage that we have in Finisterrae-3, so you can interchange information between all the systems. Of course, we have a couple of nodes for logging and one node for control the system. Let me present first of all the QPU, the quantum processing unit. Initially, the QPU had 35 qubits, but you know that this technology is still under development, so we could manage only 32. In fact, the best 32, because we have a limited amount of classical electronics for controlling these qubits. We need to select the best ones. Okay. The number of usable qubits is around 30. I will present later why we have only 30 at this moment. The technology is QASMON. QASMON is a technology for Oxford quantum circuits that has the one special characteristic is that you drive the qubits from the top and you read the qubits from the bottom. It's a nice technology because you can pack more the cables, but it has also some issues, for example, in crosstalk. Regarding the native gates, that is the most important, we support the RZ that are virtual, plus square of x for the 1 qubit gate. And in the case of the 2 qubit gates, we are using ICR. Really, we are calibrating another gate, but we publish ICR at this moment. We are not thinking, well, we are thinking, but we could not support at this moment CZ, that maybe will be faster than ECR and with less problems. At the level of programming, we support Quasant.2.0, Quasant 3.0 partially. Not all the capabilities of Open Quasant 3.0 are there. Open Pools, again, partially. Not everything is supported yet. And quantum intermediate representation. That is a standard that is coming in for the future that maybe will be or will evolve in the future because it needs some changes. This is our system. On the left for you is the picture that we have when the system is completely closed, that usually is 11 months per year. And we have on the left again the electronics that control, well, all the machinery to control the temperature inside the fridge. And the other part with the blue cables is the classical electronics that we use to use the qubits. And the other part is the nice picture of the system. Really, the QPU is not there. It's not in this picture because it's in another box on the bottom of the system. The temperature there is around 16 millikelvins. And we had this temperature during the more or less 12 months. We have later a small break due to a problem with the diluter, and now it's running since, I think, 2 months. And the idea is to try to keep the system running almost all the time. But we learned, this is one of the nice things of working directly with this system, that we need to do some stops periodically in order to make maintenance of the diluter, the user editor, not the chips of the electronic. This is the topology. And you can see that we have some red cross there. One of them is inside one of the, well, on top of one of the qubits, because there we have a very large noise and we cannot produce nothing useful at all. We have another one that is the number 0 that initially worked and now is not working. We are researching why, in fact. And we have problems with 4 connections that we cannot create something to entangle the qubits between them. And it's something that is under investigation at this moment, why we could not do, in some cases, parallel execution of the gates that we need to create these entangler gates. The fidelities, well, depends on the qubits, but usually the fidelity of 1 qubit gate is higher than 99%. It's not bad. Using randomized marking for calibrating these numbers. In the case of the without fidelity, we are around 85%, 90%. In many cases, we have fidelities higher than 90%. We want to increase this number. We try to increase to 95% or something similar, but without fidelity is something that you can mitigate easily with a very easy process. We had, in fact, higher fidelities, but they created crosstalk between the qubits, so we decided to decrease the fidelity, but to avoid problems with the other qubits. Okay. And in the case of the 2 qubits fidelities, you can see that we have always, when we can create entanglement between the qubits, a fidelity higher of 90%. That is not bad. Due to the problems of the connections, in fact, we have 4 areas or 4 islets that we recommend to use. And we are now working in one modification of our software so that you can select specifically the area that you want to run, in order to inform the compilers easily. These are the qubits that I want to use. Okay? This is information that we are publishing periodically, so in fact it's changing. If we increase the fidelity of 2 qubits gates, or we increase the fidelity of the connection between the areas, in this case we will manage this information so you can have direct access to them. Oh, sorry. The software stack, we develop our own software stack to connect the QPU with the classical node where you run your jobs. This software stack supports 2 compilers, Qiskit and Python Ticket. We have 3 backends. One of them is the QEmulators backend to simplify the access from Qiskit to the QPU. A second one that we call fake QEmulators, that is an approximation of the QPU that has the noise, the daily noise that we have measured. It's not a perfect emulator. We know that, but at least can provide you with enough information to test your programs. We have a ticket backend as well to simplify the programming using Python ticket. But if you don't want to use any of them, you can make a direct connection to the QPU, sending one of the supported languages that we have, OpenPulse, OpenQuasar, or Quantum Intermediate Representation. But in this case, you have to do the work by yourself. We have 2 ways of accessing the QPU. The one is a direct submission to one specific partition for a bad job. And in this case, you have the QPU allocated for you exclusively without any other user sharing the resources. Okay. In our case, we lose around 4.5 seconds per job. Not per job, per circuit, in order to run your circuit in the QPU. So the idea is to decrease these numbers I try to decrease to below 5 microseconds, but it's difficult. But we don't have the initial latency to connect to the QPU because the QPU is running continuously. And a second one is using interactivity. But in this case, you submit a job to this partition, so you have to wait in the queue. And after that, we have a proxy that connects to your iterative session, so you can submit and have the results, but it's limited because we are working always synchronously with the QPU. This QEmulators room interface is based on Python, but you can access as well by C, for example. And it supports, that said, this kind of open pools, open quads, and query, and the output could be raw, exactly what the QPU is producing. The number of slots is binary string, that is the usual output in many cases. But if you do your own programming of this interface, take care of the bit order. That is not the same, for example, that in Qiskit. In fact, it's the reverse order, so you have to process the output. Okay. Another important issue is this one, that is the repetition period. Because we don't have an active reset, we have to wait the relaxation of the qubits. We have a T1 around 100 microseconds, so this means that you have to wait between 300 seconds or 400 seconds in order to start the next cycle of your circuit. So we recommend not to use your own number, because we have a default number that has been calculated taking into account the calibrations, but if you want to manage directly these numbers to make experiments, you can do that. The only thing is that remember that the timing is in seconds, not because we had problems with some people that submitted in other units and finally it didn't work. Second one is QEmulators. QEmulators is a set of tools with the backends for using from Qiskit. And as I said, it supports many of the, well, two of the most used languages in this quantum computing community. So, but in any case, if you have problems, please contact us in order to fix any issue that you can have. The next thing, remember, we are not supporting jobs, asynchronous jobs as IBM. For example, everything is synchronous. So if you submit a job, you would have the solution immediately, well, after some milliseconds or seconds, depending on the job, but you don't have to wait, submit and wait for the results. I skip that. One important is the run. You can submit one circuit or a set of circuits, everything, okay? We pre-process of the system. Initially, the circuits must be compiled using the native gates. If you, unfortunately, don't submit the circuit with the native gates, you are losing time because we have to compile to the native gates. And this, if you submit a very large circuit with a very large number of qubits, this needs time because you have to allocate exactly looking for the best qubits, and you have a problem that you don't have reproducibility between two submissions. So we prefer that you initially, in other partition, may compile the circuit, and when you have a running circuit with the native gates, you start to work with the partition, the direct partition. In this case, you will do things faster, and the allocation of the QPU will be lower to host other users. Okay? In the case of open pools, you know that open pools is not supported anymore in Qiskit 2.0. Okay? So if you want to use open pools, you can do open pools programming directly and submitting to QEmulators backend or the QEmulators room, or you can use the Qiskit 1.x, so X, that in this case it has support to open pools, and we have implemented the support as well to submit to the system. We support in Qiskit both versions at this moment. In the fake QEmulators, this is a system that uploads directly the calibration of the day. In fact, the calibration is a JSON file that you can process, and we have a daily calibration system, except the weekends. In weekends, we don't have new calibrations. We have calibrations only on Monday, and Monday we calibrate the timings plus the fidelities of all the gates, and the rest of the week we calibrate only timings and frequencies, nothing more. But we generate a single file per day. So if you want to, and we have more than 300 files at this moment, so with all the history of the system. And finally, access, because this is not funded by Quantum Spain. In fact, the system was bought by our regional government with European funding. But we have committed 20% of the time for Spanish supercomputing network users. So you can apply using the open calls. The rest of the system has been allocated, reserving one part for our own research and for improving the system, for accessing the local universities and research center in Galicia, and for training new students, and we have allocated around 10%, more or less. To accessing the reserved part for Galicia, you can do it by making research, common research with the universities or with us. But you have to sign a previous agreement in order the kind of research that you want to do. So don't hesitate to contact the local universities or us if you want to work with our system. Passing, of course, the rest. And I have to say that we have a second quantum computer under procurement. I don't know exactly how many proposals we have because closed 2 weeks ago. The only thing that I can say is that the number of qubits must be higher of 48, and with another characteristics that are public. You can go our web page and look the characteristic of the new system. I hope that this system can be ready for open users around autumn next year, because must be installed around summer, and you know that we need several months to adapt and to make the initial research. And that's all. If you have questions. No questions? Yes, one question.
I want to ask on how you're analyzing the different providers to put the next quantum computer. Are you benchmarking across different providers? What's a bit of...
Well, this is a public procurement. Because it's a public procurement, you have there requirements, and some of them must be verified at the end of the procurement process. When we have bought the system and the system is installed, we have to pass some benchmarking tests to verify that the system is working as the provider has proposed during the open procurement. At this moment, the only thing that I can say is that we have technical characteristics that are public for the tendering, and we have some specific requirements that the vendor has to fulfill for the system, plus others that we would like to have. Okay? But at this moment it's too soon, because even I don't know what you know about the Spanish public procurement, but there are some steps, and we are in the early steps of the procurement. The initial proposals have been sent, but the problem is now we have around 2 months in order to make the final selection of the vendor. So maybe in 2 months or 2 months and a half, we will know the characteristics of the system and the provider.
Thank you for the talk. It's very interesting, the new kind of quantum computers, and also I think it's a very clever idea to find the way to how could I say match with the Qiskit, the procedure of how to submit the things. Maybe it will be a silly question, but when you talk about large circuits, what do you mean? How many gates? What is the depth?
Not so much.
Okay.
You know, at this moment, the problem is the fidelity.
Yeah.
Okay. Because with these fidelities, especially with entanglement gates into qubits around 90%, maybe you can execute a circuit around 10, 20 steps.
Okay. Okay.
No more. Okay. But sometimes you have tricks to improve the system.
Yeah.
Okay? But it's very difficult.
I think it's in my mind, it's a good question, because as a user, what should I expect for that QPU?
Yeah, but it's not the same to running a system with variational algorithm, where you correct partially the errors due to the optimization, okay? That circuits without any kind of optimization. If you put, for example, a quantum free transform with more than 3 qubits, I don't expect to work perfect.
Okay, thank you.
Okay, thank you for your presentation. And just a very quick question. Have you considered, since I saw the new QPU is also superconducting, if you consider adding, maybe in the long future, other hardware technologies like photonic or something like that?
Well, this is a difficult question. First of all, we need the money, and it's very expensive. The procurement of these systems is around 7-8 million euros. It's a lot of money for each one. Okay. And secondly, the problem is to have the knowledge to manage one technology is very difficult. Support 2 technologies simultaneously is more difficult. But clearly, as a supercomputer center, if we have in the future a technology that surpasses any possibilities of the other one, we will try to buy this technology in the future, because currently the superconducting qubits are not the best one in terms of fidelity, but sometimes are the best one in terms of velocity, okay? Because ions, the fidelities in the case of the ions is incredibly high in many cases, but they are extremely slow for a supercomputer center, because you need around 1 millisecond per gate. And in some cases, not all of them, and in some cases you have limited amount of gates that you can execute simultaneously. So, and the readout is even lower. So, but we selected initially superconducting qubits, and this second one will be superconducting qubits, because now we have the knowledge and experience of supporting these kinds of systems.
Okay, thank you.
Just continuing the question, kind of. Why not annealers, for example?
Why not?
Why not using annealers? Just curiosity.
There is no reason, a special reason at this moment.
Okay, thank you.
No questions? Well, thank you very much. So I think that is... Carmén. Carmén is here, so we can follow the initial agenda.
Okay, well, first, sorry for the delay. I have some problems with my college. Good afternoon, I'm Carmén, and I'm from SCAYLE. I work as HPC and quantum computing technician. And today, with this presentation, I'd like to share with you what we do at our center, the resource we provide, and most importantly, how you can take advantage of them for your research. First, SCAYLE is the supercomputing center of Castilla y León. We were created with a clear mission to help researchers, companies, and universities take their projects to the next level using advanced computing. Well, our role is not just to provide the machine, but to act as technological partner that guides and support you. Well, historically, we have three main pillars. First one is obviously high-performance computing, enormous computational power for simulation in artificial intelligence and data analysis. The second one is cloud computing. From the beginning, we've pioneered efficiency, used the IT infrastructure through virtualization. And the last one is SCAYLE, our high-speed network, which connects different institutions and provides added value service. Recently, we have these two services. The first one is one of our most impactful areas in biomedicine through SCAYLE. We provide high-performance computing, accelerates discoveries in genomic, molecular simulations, and drug designs. Well, there are projects where time really matters, so we help these researchers. And the second one is OpenSCAYLE. Science today is not just about computing, and we also need data. The researchers have many problems to share their studies, we create this service, and we provide massive, secure, and open storage to drive collaborating, and the researchers can share their datasets safely and reproducibly. Now I want to talk about our data centers. We have now two data centers designed to complement each other. Okay, one focusing on hosting and maintains the core, the HPC ecosystem, and the second one provides the network. Between them, we manage different racks, obviously the resource, the CPUs, and other that I will explain now. And we build with high availability in mind. Okay? We offer more than 99% of uptime per year. Okay, the first data center, CPD1, known as Calendula. Okay, is the real star, we will call it. And this is where our supercomputer stays, along with advanced systems designed for high-performance workload. As you can see, we have a total of 20 racks, more than 80 switches. Now we have more than 400 computing nodes that we will see. And we have a hot and cold isolate in rows calling. Okay. The second one is, as I said, we have the network part. Okay, we have 2 racks, more than 5 switches, and the servers from OpenSCAYLE. We have all data storage in this side. We also have routers and obviously the part of firewalls and more. We also have a part of backup, okay, and tape backup machine. In this slide, I want to explain the classical part. Okay, we have these nodes And it's the backbone of our high computing, of our high performance computing, ¿vale? With hundreds of nodes, thousands of CPUs, and the GPU type, as you can see in the general architecture. Okay, these nodes are provided by AMD processors, and we also use it to emulate some works, some quantum emulation. Everything runs on high-speed InfiniBand network to ensure low latency with, as you can see, NDR200. And we manage jobs through Slurm. In short, Calendula is our classical powerhouse, but thanks to these GPUs, it also brings between traditional HPC and the future of quantum computing. What's the future of SCAYLE? It's a video. Oh, well. Everything I explained are not stainless steel. The future of SCAYLE is about exploring new architectures, of course, and we are also growing physically. This is the new construction, the new building that will house 3 data centers. And importantly, one of them will be dedicated especially to emerging technology like quantum, probably if we are lucky, quantum computing, obviously. This will give our users not just more capacity, but also a testbed for the technologies that will define the next decade. In this slide, it's the same as previous one, but I like to highlight the quantum partition. This is where we integrate quantum emulator into our HPC environment. It means that the same infrastructure that runs your simulation or artificial intelligence workload can also be used to explore quantum algorithms. Those nodes are destined to exclusively quantum emulation. The first one is the Fujitsu FX700. It uses an an A64FS architecture processor, the same architecture that powered Fugaku, and I think also CESGA. Fugaku is one of the world's fastest supercomputers, and it has a total of 8 nodes, each with high bandwidth memory of 32 gigabytes. This server is particularly good at simulating quantum instructions efficiently, and it provides an environment to test quantum classical hybrid algorithms, for example. It can emulate, as you can see, up to 33 qubits. And the second one we have right now in our cluster is the emulator Evident Captiva 802. And this is based on Intel Xeon Scale processor with 64 cores and 2 terabytes of RAM. This one is straight-line in flexibility and can handle land-scale quantum circuit simulation up to 30 qubits, as you can see, and integrate, obviously, in our HPC workflow. We have in mind we need everything to integrate these nodes in our cluster, obviously. Why? Well, the emulator quantum partition. How does this actually work? Well, our quantum emulation environment brings together several layers. The first one, frameworks, for example, the users can work with familiar tools like Qiskit or Circ. Our users prefer works with Qiskit, so we need that our emulators work with that. The second, schedulers, Slurm here. Both nodes are integrated with a job management system, Slurm, okay, to perform and share the jobs. And the storage Lustre ensures high-performance data handling, just as in traditional HPC workload. So, how do you or the users can access to quantum partition? Well, first, users have to request access through res access. Once approved, you or the final users can submit the jobs after have an account with us via Slurm, and just they will work like in a classical environment, okay, in a classical HPC environment. Support is available, obviously, through both our traditional help desk and a specialized quantum support team. Finally, the users can also contact with the REST support intranet and explain or share their thoughts and their problems. They can also contact with us with this mail. And of course, none of this will be possible without the people behind it, obviously engineers, technicians, and the staff who support users on every step, every day. So thank you so much.
Sorry. Thank you for the talk. Como quieras.
Pues sí, tú dale. Si me dejas.
Bueno, gracias por la charla. Estoy interesado en esto, en lo de Fujitsu. Lo de Fujitsu es la arquitectura, que te permite emular un computador cuántico, ¿cierto? La arquitectura del chip, ¿no?
Ambos equipos.
Vale.
Ambos equipos, tanto el de Evident como el de Fujitsu, son tecnologías que permiten la emulación de circuitos cuánticos. Están específicamente diseñados, uno con tecnología de Fujitsu, el que me comentas, y el otro basado en Evident. O sea, el proveedor es Evident.
Vale, pero eso por esa parte, por ese lado. Vale. Pero por otro lado, entiendo que también utilizará técnicas como redes tensoriales y ese tipo de cosas, ¿no?
Uy, pues ahí sí.
Sí, ¿no?
Yo hablo aquí, pregunto, porque la parte técnica...
En Captiva tienes varios simuladores.
Vale, entiendo.
Uno de ellos está basado en Tensor Networks. De hecho, ahí puso que eran 30 qubits con 2 terabytes el de Evident, probablemente pueda llegar a 35 fácilmente.
Vale.
Sí, no hemos llegado a hacer pruebas.
En modelos extraordinarios, o sea, modelos de State Vector, que después tiene otros 4 emuladores, uno de los propios que escala muy bien, pero como todas las limitaciones no son generales.
Sí.
Los circuitos tienen que cumplir unas características de otro punto.
Claro, pero eso es porque la topología del chip, en este caso, del procesador en este caso, tiene... ¿Es por eso, no? ¿O qué?
La topología es un problema de que si tu circuito tiene un nivel de entrelazamiento muy alto, ¿no? Pues los tensor networks, si tienes entrelazamiento alto, pues no va muy bien. Claro,
ya. Vale.
¿Qué tipo de tensor network usa? No lo sé. Porque es que la topología depende del tipo del tipo de estructura que tenga. Sí, yo creo que el Evident soporta MPS, no estoy seguro. ¿Será MPS? ¿Multiple System o qué? Pero claro, no sé los detalles de eso. Tienen uno propio que no conozco suficiente para decir que si usan una cosa u otra. Es que eso tiene, digamos... Sí.
Gracias.
No more questions?
Wonderful.
Thank you. Now now we pass another product. In this case, it's an emulator that has been developed inside quantum space. And my name is Jorge Vázquez, that we present QUNQA.
Okay, well, hello everyone. As Andrés said, my name is Jorge Vázquez Pérez. I'm here to present QUNQA, as I put there, a distributed quantum computing simulation framework. There's a lot to unpack in this description, but we will go step by step. First of all, I want to thank my colleagues, Daniel Espósito, Álvaro Carballido, and Marta Losada, which also helped me develop this tool. Well, we are at CESGA, right? And CESGA is an HPC center. So the first thing that I want to unpack is how we consider quantum computers in HPC centers, right? And we have two main groups, as you can see there, loose integration and tight integration. The loose integration has itself two subgroups, standalone and collocated. Standalone is basically sending to a remote computer the quantum task, execute and get the results. And the collocated strategy is, as you can see there, these blue rectangles are the classical resources. You send remotely to the classical resources, which they themselves send to a remote quantum computer and get the results. So this model is not the focus of QUNQA. QUNQA focuses on the second model, on the second group, the tight integration, which also has two subgroups, the collocated and the on-node. The collocated, the user also sends remotely the quantum tasks to the classical resources, but within the HPC center, the quantum task is sent to the quantum computer. And more so on the on-node. The on-node, you don't even need to send the results to the quantum computer because the quantum computer is considered to be integrated in the classical nodes. QUNQA focus on this second part, on this second group, because we think of quantum computers as accelerators. Okay? We think of quantum computers as, for example, GPUs. We think that this is going to be the use of quantum computers, and there's a very strong current of thought on this matter. Okay? And the second part of the description of QUNQA, I said distributed quantum computing emulator framework, right? So what is distributed quantum computing? This is very similar to classical distribution. You want to parallelize some tasks to execute in a parallel way, right? And there are three ways of doing this in quantum computing. The most naive one is this one that you see here that we call embarrassingly parallel. There are no communications whatsoever between the quantum computers, and this is a classical distribution of quantum tasks. You just send, you see here 4 QEmulators, but each one can be different computers. I put the image just for corporative purposes. But they can be different. You can send one circuit to the first one, another circuit to the second one, or the same circuit to both, but with different number of shots. This is classical distribution, right? The second one is classical communications. In this case, you have the quantum computers connected, but just through a classical link, right? You can send a bit, a classical bit, and this classical bit is going to affect the execution on the quantum computer that receives the classical bit. Sorry. And the third part, that is the quantum communications. In this case, the quantum computers are connected, and what we mean by quantum connection, we mean that, or quantum communication, we mean that two qubits, one from one QPU and one from another, can be entangled, okay? This, from the simulation standpoint, is more difficult because once you have two QPUs connected, you need to simulate both as a whole, as one QPU, okay? Well, just to sum up, we have the simple model, the classical model, and the quantum model. We're going to name them this way to keep it simple, okay? And thinking about QUNQA, what does QUNQA intend now that we know all of this preamble? Well, we need to emulate these different models in an HPC center with classical resources, okay? Now, talking about the corporative image, what is this? This is a virtual QPU, because we're talking about emulating quantum computers, right? So, what do we mean by a virtual QPU? Well, this is classical resources, and these classical resources are composed by three main components. A server, which is listening constantly to quantum tasks to execute, A backend that is basically the information of the quantum computer that you want to emulate, the noise, the topology, the gates supported, and so on and so forth, and the simulator. Simulator that is responsible of simulating the quantum task. Nowadays, we support 3 simulators. AIR, you probably all know AIR, MQTT-DSIM, which is an emulator from the Munich University, and also QUNQA Simulator, which is a simulator that we developed to kind of play around with things and test how things would work, especially with communications. It works correctly, but probably not as efficient as AIR or MQTT-DSIM, because it was not the main target of the project. Nowadays, we have the 3 models installed in the 3, available for the 3 simulators, okay? But QUNQA is modular. We could add a simulator and, for example, only support the simple model, or support the simple and the classical. Of course, if you support the classical, you support the simple because it's a subset, but it could be other, let's say, in increments, right? Now, you're probably asking yourself, how do I set up these QPUs, these virtual QPUs? How do I interact with them, right? How do I use QUNQA? At the end of the day, you want to use this tool. This tool is for you, for the users. Well, first of all, to set up the virtual QPUs, we implemented some commands, we think are useful commands. QRaise, which is the most important, and it is responsible of setting up the QPUs, the virtual QPUs. QDrop, which is responsible of removing relinquishing the classical resources and make the resources available again for every other user. And QInfo, which gives info about the QPUs that you just set up with QRaise. Here you find some examples of the commands, but these are very naive examples. The most important one is QRaise, and we will delve into this. QRaise, as I said, is the responsible of all the commands of setting up the QPUs, and the flags of your interest are there. The number of QPUs that you want to set up on one single execution of the command. Of course, you could execute QRaise several times, and you could stack all the QPUs, virtual QPUs, of course. The maximum time, which is with the /t, you want to get the QPUs running X amount of time. You specify it there. And then you can specify the simulator, as I said, AIR, MQTT-DSIM, which we call Munich for simplification, or QUNQA simulator. You can specify the backend of the QPU. As I said, the noise model, the gates, and all of these things that define how the QPU works. And also you can specify if you want classical communications or if you want quantum communication with these 2 last flags. Okay, and now how does the user interact with QUNQA, with the virtual QPUs, right? Well, we developed a Python API that builds on top of the C++ backend, because QUNQA is all, in order to connect with all the simulators, QUNQA is built in C++. But the Python API, in order to be more user-friendly, is built in Python. And it is basically responsible for the creation of the quantum tasks and the connection with the virtual QPUs, okay? And if you remember, the virtual QPU was nothing more than a server, so it is responsible to connect with the server and send the quantum tasks. Let's see an example, because everything is more easy with an example. And there you have our getQPUs function, which is part of the API, and it is responsible of getting the devices that you raised with the QRaise command. Okay, this is very similar. If someone is familiar with OpenCL or CUDA, this is very similar of how these frameworks work. You just get the devices, you choose one of the devices, and you execute the quantum task in that device. And this is precisely what we do. As you can see there, QPU 0 run the Qiskit circuit, because we support Qiskit circuit. Okay, you can create a Qiskit circuit and execute it on QUNQA. You can transpile also. Nowadays we transpile using Qiskit. We have that dependency. We could add another transpiler, of course, because as I said, QUNQA is modular. And you could get the results and print, for example, the counts. Now we are returning the counts and the time taking of the simulation. Now, this was the simple example. If you want to add, for example, classical communications, right? You could do the same, you could do the get QPUs, but you can see there that we did the QRace on the Python file. This is also available. You can do the QRace command on the terminal, but you also have the functionality of adding the QPUs directly on the Python script, if it's more convenient. For example, if you want to do a variational quantum algorithm, maybe you want the whole task to be executed, the classical and the quantum, and get all the results. Now you create two circuits. You see there the first one and the second one. And of course, they can have an arbitrary number of operations, but there we just show the measure and send and the remote save, which are the classical operations to communicate to QPUs. And you would then add in a list the circuits and execute it with the run distributed directive. Of course, put in the circuits and the QPUs that you want these circuits executed on, of course. And with the gather, similar to MPI in this case, the gather function gets all the results from all the QPUs, and you could do with them whatever you want. And also the qdrop command is also available in the Python script. And now with Quantum, maybe you didn't even notice any change. We just changed there in QRace the flag and the operations executed. So you can see better. I have them highlighted. But in this case, we have a QSend and a QReceive. If someone is familiar with DQC, this is just, in this case, it's a teleport protocol that is implemented in the backend. Okay? And that's all for me. Thank you very much. Any question? I was a bit too fast, but.
We have 12 minutes because the coffee is not ready yet. Questions?
I forgot to mention that this tool is available at CESGA, but we are interested in installing it on another supercomputer. That's it.
And in fact, will be in other RED centers, maybe before the end of the year, because we have centers that has to install the system there and test it. And we are open for collaboration. This means if you want to put your software there or testing or something like that, we are open to collaborate or making new capabilities for the system. It's part of the first session with the last presentation, but not the least, with Irais that will present one of the emulators that are available in CESGA, that is the one of the Spanish Supercomputer Network Center. Irais, the floor is yours.
Thank you, Andrés. So, as Andrés said, my name is Irais. I'm working as a Quantum Spain technician for Quantum Spain and coordinating these efforts. Okay, so I will present today one of the simulators that we have available in CESGA. So the name is QULACS. This is a high-performance quantum simulator writing in C++ with Python interface, and is designed for speed on CPUs and compatibility to GPUs also. So we have support to pure state emulation and complex quantum circuits. At CESGA, we have the classical nodes with an ARM processors that are crafted to achieve this high efficiency in quantum emulated jobs. So this is our CPU that works with Fujitsu A64FX IRM with a state vector. And also we have one processor per node with 48 cores. And those are organized in 4 groups. It has 32 gigabytes with a high efficiency and high bandwidth memory also. The memory is larger than 1 terabyte. For each processor, that is subdivided into 4 core memory of groups of 12 cores each. And we have, as I said, full support of scalable vector extension. And we have you can check this specification with these 2 commands lines. You can put S-control show node and cat CPU info, and then you can see the full description of the architecture. So what are the advantages of using these nodes with QLights? We have a high parallelizable quantum emulation, so this will be ideal for multi-thread environments with high bandwidth. The support for vector instructions improves linear operations on amplitude vectors, and also we have low energy consumption per operation. So also the resource is isolated and is predictable in performance. At CESGA, we have this module availability by modules or by singular uptime. The installation is with multi-threading support, and it optimizes the compilers. We have the compatibility with Python scripts and also with C++. So the basic usage of QLACS, this is displayed in A64 module 3. So since they do not share the same module 3, the model is loaded when we access to these A64 nodes. And this will be in SPatch. So this is a basic example of the usage of QLACS. We will now see in real time. You can find in the documentation a submission template where you can see all the parameters that you can tune for your script. And well, as I said, it is available only from the A64 nodes. So you can access through them with SBatch or to compute in this node, A64. But there are also available modes at the nodes of ILK that we have in CESGA for computing, but these are not working on the architecture of A64 nodes. So these are only working, well, this is also available, but not working on the architecture. If you want to work with the architecture, you have to go to the A64 nodes. So here we will see, sorry, I go through. So I will show you briefly how it works. So this is a simple script that where we have to define our the partition is in A64, as I said, and then we can describe the number of nodes that we need. Also, we can schedule the numbers of tasks per node, and we assign the number of cores, the time limit, the memory per CPU, and then we can just simply do module load QLAX HPC. This is the name of our module where you can find this simulator. And we have here as a simple example run a Bernstein-Basirani algorithm with MPI. And we just simply do this batch. Just here we are in the A64 node, just to remember that. You can do just compute or batch to that. So here is we can see that it's running. It takes a bit. Okay, so now it's finished. Here we have the result, and this is a number secret that defines the algorithm with the number of qubits 30 and the number of global qubits 2 and local qubits 28. So we have, as you say, is quite fast, and this is you can compare. We have also compared here. How the efficiency by running in parallel or in a single way, and you can see the wall time MPI is 80 seconds compared to the serial wall time of 21 seconds, and it was done for 30 qubits also, and well, with the same algorithm. And just to show that. If you want to, as I said, you are able to use it also you are able to use it also in ILK nodes, not in the architecture of A64, but here you have also these modules that have the option with the interface of QLAX, PennyLane, and Qiskit. Also with MPI, those three. And here we have an example of, you can also do your notebooks. This is an example of a circuit with the PennyLane. This is a circuit bell basic with PennyLane that we have done there, just a simple example. And also with Qiskit, here is we have sample, well, we have construct a circuit of 5 qubits, and then just sample all the states and measure those with the higher frequency, the 20 first with the higher frequency, and this is the interface with which just some of the examples that you can do here with the QLAX. So as you see, it's very friendly, and if you need any support, or if you have any questions, sorry, on how to implement your code or anything else, you can contact support at CESGA.es and also with our teams that work for Quantum Spain. Okay.
Questions? No? Thank you very much. It's just in time, just o'clock. We move to the next session, that in this case the moderator will be Naya. So, the people that participate here.
So, hello. We have just finished the presentations about the infrastructure available in quantum computing. Now we are going to hear to some experts talking about their projects, where they are working on. And we are going to speak about 4 different topics. So let's start with the first one. These 4 speakers are going to speak about their projects in mathematical and algorithmic foundations of quantum computing. First of all, the speaker is Antonio Falco, that is a researcher of the University of Cardenal Herrera, who is working on a mathematical model for a universal digital quantum computer. So, whenever you want.
Yeah.
Okay, thank you. Okay, I explain you briefly, no more than 3 minutes, what is my research. Okay, wait. Okay, what is the challenge of my group of research? A long time ago, I was the director of an industrial chair. So my industrial partner asked me what are the capabilities to a quantum computer to simulate some kind of industrial process. So at that time, I started to work in this business because my past research was essentially in the mathematical foundation of tensor networks and tensor spaces. Okay, so my first impression was that there are a lot of hard work to perform here about the standardization of this business. In particular, the current formulations lack of a unified probabilistic framework, because it's not the same classical probability what quantum probability that for my colleagues, my probabilist colleague call algebraic probability. Okay, so the idea is to develop a mathematical model of a universal digital quantum computer, but based in 2 ideas, is algebraic probability and geometry. Why? The first reason is that quantum computation indeed is related with the unitary group actions in the rank 1 matrix, rank 1 density matrices. Okay, the theory of rank 1 density matrix in tensor theory is a very well-known business that and it allows to recover one of the more important properties of this part of mathematics to understand how we can construct quantum algorithms. Okay, the second one, and for me is the key point, is a rigorous definition of quantum circuits. Okay, for me this is the key point. Why? Because people say a quantum algorithm is a unitary matrix composed by unitary matrices. So what is the differences between the quantum algorithm or his inner part? So for me, here is the milestone of all these problems. The reason is the following. Of my business is numerical analysis. In numerical analysis, people know what is an elementary operation. So if we ask you what is an elementary operation here, there are no consensus. Here I see 1 qubit and 2 qubit gates. But what are the mathematical definition of that object? There are not. Okay? So, and one more thing is the integration of this business in the probabilistic framework. Okay? So this is the good news because there are a lot of work. So I meet along the coffee with Andrés. I said it's good because our salary are sure. Okay? Well, and, excuse me. So here in our group, we obtain some partial results. The first one is we now have an algebraic definition of elementary gate. Okay? So the good news is every gate that you know, what you use in the is an elementary gate, but not all. The bad news is that there are two kinds of different definitions. I explain you. There are two kinds of approaches. The first one, in tensor theory, is the same. You have a dual approach. It's algebraic against topological. What is the reason? The reason is that we can perform all these things from using algebraic theory. But, for example, the bad news is the well-known theorem of Solovey-Kitaev. Solovey-Kitaev is a topological theorem. It's not algebraic. So there are two approaches, and it is related to how we can see the unitary group. Okay? So for the moment, we have two different definitions of elementary gates, algebraic and topological. That allows to, for example, the well-known Gruber-Rudolph algorithm. Now we are to be able to give a mathematical proof that this theorem is reality true. Because if you take the paper has only 2 pages. So in 2 pages, it's impossible to prove it. Okay? There are another approaches which is related with geometric analysis of this business because the unitary group is a manifold. The geodesics in the manifold implies that you, in some sense, you have good algorithms. If you see an algorithm as a geodesic in this group, also we can perform a statistic analysis. That means we can check also that the probabilistic foundation of Regev algorithm is the multivariate version of the short algorithms. Okay, so we in this place we obtain 2 interesting probabilistic results. The first one is related with the so-called concentration of probabilities, and the second one is something about indistinguishability theorem. That means that we can, in the indistinguishability theorem means we can choose classical probabilities, and then we can, by using a quantum algorithm, we can construct a probability which is indistinguishable with respect to the classical one, okay, with certain level of accuracy. And the next business is related with the study from the point of view of statistical properties of open quantum system or system with continuous spectrum. So that is the equivalent of random, continuous random variables. Okay? So well, we find because it's better to discuss. Okay? What is the next step? The next step is to put all together. Oh, yes. No, I could that. It's better. This is my USB. Okay? So the perspective is to put all this mathematical machinery into a quantum computer. I think, yeah, and this is my opinion, because when I work in numerical analysis, we perform in paper, we perform the algorithms, and next we go to the computer to check if the theory runs. Okay? In this business, when I start to work with it, we take only the computer to perform the algorithm, but we don't take the hand to write algorithms. Okay? So the bad news is that we start. I think that because I very old. I don't know the end of this business, but I am happy because I see the starting point. Okay, thank you. This is all.
So thank you, Antonio, to share with us your research topic. And now, are there any questions for him? No? If not, yeah, Andrés.
Thank you. Just a single question. I have many questions for your presentation, but one of them is that the definition of a circuit like a unitary matrix or something similar to it. But the problem is when we have mixed with measurements, we don't have unitarity.
Yes.
In this case, what kind of definition can we have about this kind of circuits?
Indeed, the idea, Andrés, is the following. If you consider the algebraic one, the tensor product of several unitary matrices is an elementary matrices, algebraic. But if you take the topological one, the problem is that the topological is related with the following. You can see an elementary gate as an element of the unitary group of 2 dimensions. Okay? So you embed this in the unitary group of n dimensions. In algebraic, there are no problem. But in topological, because you have two manifolds, when you take the derivative of tensor product of those unitary matrices is the sum. So this is don't respect this is not an isometry. And you lost this property. And then, in this case, there's not an elementary gate. So only elementary gates in the topological framework are gates with essentially are one unitary matrices, the tensor product of the identity.
Okay, thank you.
It's clear.
Any other question? No? If not, let's move to the second speaker. Andoni Zozaya is a researcher at the Public University of Navarra who is working on a project called Random 2 Generation in Traceless Matrices of dimension 4. So, Andoni, the floor is yours.
Yeah, I think slides should be here. Okay, I was told that I have to do it in English, but the slides are in Spanish, so we will do it in that way. Okay. I don't know if this works. Yeah. Okay, our background in our case is just pure mathematics. It's asymptotic algebra. And in asymptotic algebra, we always have like families of finite algebraic structures, but they always come in infinite families. So in theory, if we will have an infinite computer, we could give the information about this structure to the computer and obtain any information we want. But actually, there are limitations. So many times to prove something, and before having a formal proof, we have to test them in the computer, as Antonio said. No? And the experiments and the testing in the computer won't give us usually a proof, but just an intuition or a pattern, or sometimes it also can give us contraexamples, like some theorems or some conjectures that right now are unknown. In few years, usually when the computational capacity increases, then they are proved. This is just, I think, the first example of something that was conjectured in the 18th century by Euler, which is like, okay, if I have an n power, a power of a natural number that can be written in a non-trivial way as a sum of n powers, I mean, with more than one term, then he said that, okay, at least you need at least n of them. And just with one of the first computers with a CDC 6000, it was proved that this conjecture was false just by giving this identity. This by hand cannot be done, but with the increase of computational capacities, it was done. With quantum computers, we don't want to increase the computational capacity, but to use algorithms that quantum algorithms, no? And so, in our case, with Javi and Marisol, who is not here, like the conjecture that we are looking for is the following one. The structure we want to study in our case is simply SL4 over a field of characteristic 2. This is just simply matrices of 4 times 4 matrices. And the field we are considering is a field of characteristic 2. The usual one, F2, is just a field with 2 elements, 0 and 1. And you have an analog of 4 elements, which are polynomials in 0 and 1 if you want to see. And like, this is like a small piece of a bigger theory, which is like a generation in simple algebras. But we have the conjecture like, what happens if you take two random elements in our vector space of dimension 15, and you consider the Lie algebra they generate? Okay, the vector space endowed with an extra Lie bracket. And just if you, with a classic computer, you do some experiments, you take some random matrices. It seems that up to change of basis, this is isomorphic to a Lie algebra of matrices size 3 times 3. Like if I have to do a picture, then the subalgebra generated by two elements seems to be stacked in this upper corner of 3 times 3 matrices. Okay? But still, this is a conjecture. And we want to prove it, but before doing that, we want some evidence, like that some approximation of this probability of this sequence of probabilities. Okay? So, if just for doing it for brute force, we have a big abstraction, which is the size of this algebra. This is a vector space, even in the simplest case, which is the field of two elements. Then this is a vector space of dimension 15. It has 30,000 elements, and so we have to study all the pairs, the structure they generate. Okay, it's too big, it's not doable. Thank God we have algebraic reduction we can do, like, okay, we have an algorithm that actually using that joint representations in the algebra, we can see like an algorithm to describe the algebra they generate, okay? There is an algorithm where we are adding elements one by one, and we have to compute the dimension of the vector space that we have till it stabilizes. In our case, the matrix is 3 times 3, since the trace should be 0, this is the condition defining, are something of dimension 8. And like we want to study, like we want to test for random elements, like whether the dimension is 8. Of course, this is not a sufficient condition, it's just a necessary condition, but it's just to get that. So we want to test some linear problems, which are just that, okay, I'm adding elements one by one. When I'm adding them, it's already in the set of elements I have generated. It's a pertinence problem. But also, since I want to test linear independence, then I have to compute the rank of a matrix. This is just simply that, no? And so we want to, classical computers have some instructions here, and we want to try to get some advantage here. Like in the, and here, for the problem of the rank, for example, over the complexes, we have algorithms that help on that, no? We can use some encoding, some matrices. Here it will be like 7 times 7 matrices over F2 if you want. And there we can compute like singular values with the SVA. Okay, and in theory, this quantum algorithm that improves the classical complexity, which will be just using the Gaussian method, this is of n cubed, to something that is a logarithm of the a polynomial in the logarithm of n squared divided by the error. Okay, this is in the complex setting. We want to do it in the F2. So, okay, it's not clear that this will stand clearly, but since we have approximating a probability that also, like another valid stuff will be like the QAE, that also in theoretically the searching complexity reduces quadratically. This is what I want to tell. Thank you.
It's really interesting, the topic. Are there any questions for Andoni? No? So let's move on to the next. Okay. Sorry.
No, it's about your Krylov space.
Yeah.
You take all the combination of the adjoint.
Actually, it's not direct.
And the powers, or
no? It's not actually the combinations. There is an algorithm done by Boyce like 20 years ago, which gives you like an algorithm to check what's the dimension of the algebra generated by two elements.
No, but it's not for me. No, the problem is the algebra generated. You take two elements, x and I, and then you take the add of xi, which is the different Lie brackets of two elements.
Product.
Okay, the product. But there are those three. The question is, if when you take the Krylov method, you take the exponential of the matrix to compute the different subspaces. Here you take the powers of x and a.
I don't take powers. I just take an adjoint.
Okay, only that.
So it's like two products. I have to do in each step. Okay, that's why.
Okay. Any question? No. Okay, so let's move to the next speaker. Guillermo Rivas from Irais Institute is going to tell us about Regev's algorithm implementation. So Guillermo, whenever you want, whenever you are ready.
Thank you. Okay, so hello everyone. During the following 7 minutes, we are going to talk about Regev algorithm, the implementation of Regev algorithm, and why this is an interesting thing to do. So we are going to do so following this index here. First of all, we are explaining what is integer factorization problem. Basically, given a number here, 35, we have to guess integer factors 7 and 5. This is basically the problem of integer factorization. So this is an easy thing, but not so easy, because for the best known classical algorithm, the complexity grows exponentially with the number n. We have to do the factorization here. And this complexity is very important for the point of view of security, because security of cryptographic algorithms, such as the popular RSA or EC, are based on the complexity of this mathematical problem. So if we find an algorithm to do this task better than this, for example, in polynomial time, this security will be break. So here we have to talk about SOR algorithm. It is a quantum factoring algorithm based on the classical reduction on the factoring problem to the problem of order finding. So basically, if we find this order, is the same problem as do the factoring, the factorization. We are going to do this example here, for example, with 35, the same number as before. We pick a random integer from a to n, for example here n, and we compute the modular exponentiation modulo 35. So for example, 9 to the power of 0 is 1, to the power of 1 is 9, to the power of 2 modulo 35 is 11, and so on. So the order here is this R, the power we have to put here to get 1 modulo n, in this case is 6. So from here to here, 6 steps. So once we have this R here, just do this operation, greatest common divisor, and we get easily the factors. So for example, if we put 6 here, 9 to the power of 3 is 29 plus 1, 30, and the greatest common divisor between 35 and 30 is easily 5, and so on. Okay, so basically, SOR algorithm, this quantum circuit here, and after this quantum circuit, we get an output of this type, and after the classical post-processing, which is a continuous fraction algorithm, we get this R with a complexity of polynomial time, so better than the most efficient classical algorithm. And after we get this R here, we easily find the prime factors. Okay, so now we can move on to Regev algorithm once we understand the SOR algorithm. So as Antonio mentioned in the first talk, very quickly, the Regev algorithm can be understood as a multidimensional extension of a SOR algorithm. We do here the same example of a factorization of 35, and instead of one dimension, this is the same example as the previous slide. We now have 2 dimensions, 9, and now with 4. And here, as you can see in this grid, the order in 2 dimensions is not 6 here or 6 here, but is 1, 1 in 2 dimensions. Because we have only to move 1 in this axis and 1 in this axis, and we obtain the same one, what we are looking for. So R is 1, 1 in 2 dimensions. We can compute this. Now we have 2A, the same as before, 9, the new A here, 4, and we have 2 R's. So 9 to the power of 1 over 2 times 4 to the power 1 over 2 is 6, 6 here, 6 plus 1 is 7, is the same with minus here, 6 minus 1, 5, and the greatest common divisor between n, which is 35, the number we are trying to do the factorization, and 7 and 5 is easily 7 and 5, the prime factors of 35. And why this is important? Because as you can easily see in this grid, intuitively, and there is many tricky things here, but you can see easily that it's more efficient to move in 2 dimensions because R is nearer than moving in 1 dimension in x-axis or y-axis. So this is one of the reasons why Regev algorithm is more efficient than SOR algorithm in terms of number of gates in this problem of integer factorization. So finally, the goal and needs, well, so the goal is to compare the performance of SOR and Regev algorithms in the context of noisy quantum hardware and prove whether the Regev algorithm provides better results or not. If we have less gates, the result should be better. And of course, the main resource needed for this test is a sufficient number of qubits to test the factorization of several integer numbers in order to assess the scalability of both algorithms. And that's it. Thank you.
Any questions for him? No? So, Guillermo Rivas.
There is one question, I think.
Ah, sorry.
Sorry? Well, as much as possible.
Yeah, but can you give us an estimate that might work for this?
Not only to do the factorization of 15,
Okay,
I think.
Okay, if there isn't any more, yes, there is. No, okay. Sorry. So the last speaker in this topic is Arturo Rodriguez. He came from Beside Research Group, and he's going to speak about the quantum iterative approach to the traveling salesman problem.
Well, hi everyone, I'm Arturo. I'm a researcher and a PhD student in Visitor Research Group, University of Salamanca. And I'm here to talk about our implementation of this iterative approach to the traveling salesman problem. I guess you have all heard about the traveling salesman problem, but if you don't, it's just about you have a number of cities, so you have to go through all of them in the shortest route. That's the point. Well, I have decided to include here in Algorithmic and Mathematical Foundation. It's not so mathematical as the other ones, but I guess it's quite interesting because it's a combination of these two well-known algorithms that I'm sure you all know, that is quantum phase estimation and Grover amplitude amplification or Grover search. No? We are going to combine both algorithms in order to solve the TSP in what we think it could be an efficient way if some technical issues are solved. No. Also, I can say that this algorithm we are testing here can be used to other optimization problems just with few changes. No? Okay, but how are we using these algorithms? No? First point will be calculating root cost. No? Well, the main idea here is calculating root cost and then narrow the solution space to the point where we just have the less costless, or the costless route, no? The route with less cost. So we need, let's say, a pre-algorithm who calculates all costs and then the point of narrowing the solution space. Well, you see here some mathematics, but the point is you can interpret the feeder as the cost from traveling to one city to other. This is a 4 towns example in order to simplify everything. No? So we have here the cost of traveling from one town to other, and we can create an operator. You can see there. I'm not going to explain all encoding because it's quite tricky and we don't have so much time. No? But you can sum the phase there up here, and you can see it's the sum of the cost of going from town 0 to 3, 3 to 1, 1 to 2, 2 to 0. The encoding is quite tricky, but you can see that we have created an operator that is obviously unitary because it's a diagonal of exponential. And using this operator, we get as phase this root cost. So we have gained our first part. After using phase estimation with this operator, we can have this state we have of the bottom of the slide. Just as a reminder, people usually think that quantum phase estimation, you have to have the eigenstate in the lower register. No, you know it. But it can be, as it is done in source algorithm, it can also be a superposition of those eigenstates. So you can create this state here that is just a superposition of all route and all routes and its costs. No? Now the point is how we can narrow the space of this to get just the route with the less cost. No? Well, we have used a modification of Dury-Hoyer algorithm. I don't know if you have heard about it. It's an iterative process in which first we can measure this state, and we can, as you know, if we measure this state, we have one route randomly selected with each cost. So we use that cost as first threshold, and then we use amplitude amplification to amplify all routes that had less cost to that threshold. So we can start there an iterative process in which at each iteration we are getting a solution with with equal probability of the states that have lower cost than that route that we first selected. With that, we can continue that process until we reach the minimum, and that's all. Okay, that's mathematics. So what can we do to implement that on a real quantum computer? Well, if you have just seen just the root cost, for example, had 8 qubits, we mean that it's really, really difficult in actual hardware compute this algorithm full or completely, but we have decided to chop it in different parts in order to check different parts of it, how they work. I like to say that one thing is mathematics, another thing is what you can do, and later they have talked a lot about, well, earlier they have talked a lot about translation or how we can get from these unitary groups to the real quantum hardware, and it's really difficult. When I've been trying very hard to implement these gates ad hoc in the hardware in order to perform trickly all the states. Just to say this is simulated, we haven't figured out how to do it, but I will say I'm optimistic about it, so we will make it. But we have like chopped it in different parts, and here we have like the first creating the superposition. Here we have another part that is calculating one cost, not all of them at the same time. So we believe we won't be able to perform the full algorithm, but I am optimistic about creating different parts of it. And that's all. Thank you for your time.
So, well, any questions? No? I would like to ask, not you, the fourth of you, as we are here in the JURES, I would like to know if you have some necessities, some special necessities, or maybe another kind of infrastructure for your researchers. So it's the time to speak about it with us, and we will try to solve it. So, any of you? More qubits, maybe?
No, the more important needed is time.
Time.
Time for us, not for the computer. Yeah. Because, no, it's my experience with this year about SCAYLE and CESGA is nice, but I take a lot of time to perform everything, because sometimes I take my computer, now I try to go to the QEmulators, so the first say no, 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 no. The problem is that you need to take SSH without user in time that you are. This is okay. All right, but the pet is a little trick, but the problem is that if you have a lot of time, it's not my situation, so it's the only thing. But I think the resources are nice, but the problem is that we need a lot of time. Mm-hmm. But young people is different.
Yes, the microphone, please. Here in the front.
Thank you. Could you elaborate more? Because time for us is maybe different than, for example, because we have time for accessing the GPU, the allocated time.
It's not for accessing, it's time for our institutions.
Okay.
Okay, because the problem for researchers, when you when you take only theoretical research, there are no problems because you are at home. But the problem for people that work in both worlds is that you need to take your time to write your equations, and next you go to the computer. Okay, so usually I don't know, because it's in my case I have some kind of standards to run the things or to perform the things. When you go to another place where there are a lot of different things, you need to take a lot of time to adapt to this.
Okay. Have you used our support system? Because we have technicians to help you to do this kind of work. So maybe one possibility is you contact your research center. Well, research center, no, the close Spanish supercomputing center. There is one technician to help you to do these kind of things.
No, I take a mail when the water is like this.
Yeah.
Okay, but I think in my experience is good, because when I have a lot of all work in Linux, When you have some trouble, you check in internet, in 5 minutes you have some kind of solution to your trouble.
Okay.
Here is a little bit complete, is natural, okay, but it's not the same.
Okay, thank you. Actually, that's why I meant in one of the first talks about the community, because community, Stack Overflow, for example, is one community.
But here is not, because the problem here is that the hardware is very new. There are no a long history about this, okay? Because I meet a lot with Andrés. In my university, we buy a toy quantum computer, okay? For little experiments runs well. Yep. But I take a lot of time to understand this because there are no historic about it. Here we have more or less the same problem. I think that in the future, the community increase the information, wrote in a lot of very good documentation and so on and so on. But at this moment, we are the pioneers in this business. It's good, but it's not.
No, yes,
not easy
actually,
for us.
The idea that I had in mind with the community word, it's essentially is like even the community can support other people in the community. So that not just the heads of the research. Like if you don't have time, maybe another person had the same problem. You go to a forum and you watch for the I don't know, something like that. I mean, I know that it's difficult because actually we in the Basque Country we are trying to do. We are doing that actually with the Basque initiative in the 3 provinces in Euskadi, and it works actually. We create kind of with the time, obviously, with months of doing the things. It takes time to make a network that the people help each other.
Yeah, I understand. But for example, in our case in Valencia, it's complicated because
it is.
We are. Okay. We start to growth, and the pioneers are the pioneers.
Okay, so let's move on to the second topic. Now the following experts will introduce us to the field of quantum machine learning and artificial intelligence. So please, the speakers came here. Thank you. Sorry, thank you all the speakers that have been introduced into their research. So the next presentation is Borja Ispurua from Multiverse Computing. He will present his project of quantum large languages. And so when you are ready, the floor is yours.
Hello. Okay, so my name is Borja Izpurbaltuna and I work for Multiverse Computing in San Sebastian. I work as a senior research scientist in the research department, and I'm actually researching on the intersection between quantum and LLMs. So one of the main questions that Multiverse is trying to address right now is the huge increase in electricity consumption that LLMs are gaining. So as we can see, the amount of energy needed to train these LLMs is increasing exponentially, and this is only going to be increasing in the next years. So this is a huge problem right now in the world, and we are trying to make research and so on to try to address this problem. So actually, we are also having the IBM quantum computer in San Sebastian. We are actually building an ecosystem, and we have many projects and many partnerships with them. So this is also one of the main attractions for this project. At research in Multiverse Computing, we are also researching on different topics, not only classical AI, but also tensor networks, quantum AI, and we have multiple papers on those. And this is one of the most recent and most impactful papers in which we present Compactify, which is one of the newest products from Multiverse. And in this case, this product, what it does is compress LLMs and reduce the number of parameters. And by this, we also reduce the number of, well, not only the electricity consumption, but the memory use and these metrics. So one of the main questions is, would actually quantum help in this case? So at Multiverse, we think that, well, we use quantum-inspired techniques for this compression, tensor networks, and we think tensor networks are the middle step, the intermediate step between classical AI and quantum AI. So we think we are already in the intermediate step, and we are close to the final step, which would be a quantum LLM. We are not yet there, but we think that could be the future. So in this case, I'm going to present this quantum transformer idea. There are two main ways or paths right now in the research area. One is the PQC, the parameterized quantum circuit based quantum transformer, in which basically you try to replace or you try to add or you try to encode some data in quantum circuits. And this type of paths or this type of ideas are actually quite NISQ friendly. So this means it can be implementable right now or in the short term, whereas the other path is the quantum linear algebra-based quantum transformer, which is in this case more related to matrices and trying to do this multiplication operation more efficient. So this is more for the long term, middle term, long term, as it requires fault-tolerant quantum computers. And these two are the main paths. Actually, at Multiverse, we are right now quite focused on the first one, parameterized quantum circuit, because we want to get some impact in the short term, but we are also doing research in the background in the second path too. So with this, I present one of the papers we released some months ago, which is quantum large language models via tensor network disentangles. So in this idea, what we do is we take one of the LLMs matrices. This could be a self-attention layer, it could be an MLP layer, and we decompose it using tensor networks into an MPO. This MPO can be further compressed into another MPO with a lower bond dimension, which is the amount of entanglement, this MPO, the amount of correlations, the amount of information from one node to another that it has. And it has some extra unitaries that we call the disentangles, which, because they are unitaries, they are naturally implementable in a quantum computer. So in this idea, what we do is we replace the classical MPO with a hybrid classical quantum MPO in which we have some unitaries that are implemented in the quantum computer, and then the MPO that is implemented in classically in the same way. So this is one of the ideas that we published some months ago, but we are also researching on different tracks and different ways. So just to end, some other companies that are also investing and researching on this. So this is not something like really, really new, but a lot of companies are looking into this. And that is also why we think that the quantum LLM is not yet implementable, but it will be in the short or mid-term, as long as we improve in the research and also the quantum computers improve in their error rates. And with this, I finish my presentation. Thank you.
Thank you, Borja. It's really interesting topic. Are there any questions for him? No? So next speaker is Rocco Belester Benito, and he will tell us about the quantum federating learning. He's a researcher from CESGA. The floor is yours.
Thank you. This is the computer, right? Yes. Hello. Okay. Hi, everyone. Nice to meet you all. My name is Rocco. I'm a PhD student from Barcelona, and I'm doing research in quantum computing in the Artificial Intelligence Research Institute from CESGA. And, well, I must start by saying that I'm actually an industrial PhD student. So that means that I work for a company. This company is called Strategic Platform. It's a little consulting firm from Barcelona, although they have offices also in Madrid and in Lisbon, even recently in Mexico, I think. And they were really interested in seeing how quantum computing can be of use in two distinct topics. The first one, of course, is optimization, because it's a consulting firm and they optimize 24/7 everything. And so far, I've focused on optimization with quantum annealers. And if you're curious, we have this paper from a conference last year in which we tackled the three-shot problem, the satisfiability problem, which is a canonical optimization problem. Really interesting because it's NP-complete and it can be translated to multiple optimization problems. And we did several experiments using the Waves quantum annealers and got nice results. So if you're interested, there's the paper in there. And the second topic that we are researching is something called federated learning, which is a concept that came around about 7-8 years ago by Google. The guys at Google realized that had two problems because they wanted to train machine learning models which are in general data-driven, but they have a huge amount of data that cannot be centralized. It's really difficult. And also, they care about privacy. I'm not sure if they really care, but European Union really cares about privacy. There's a lot of regulations going on, so they came up with this architecture, which is called federated learning. And I want to briefly explain it. You can imagine that you have a set of parties. You can imagine a set of hospitals, maybe, that want to train a classification model. And they want to have as much data as possible. But there's the problem that patients' data is confidential. And it cannot be centralized or shared in any way. So what they do is they train locally. Each hospital trains with each local data, and then they share model parameters or gradients. And these gradients are averaged, for instance, in an external server, which computes a global gradient, if you might, and send this back to the clients. And this is an iterative process, and it converges nicely, depending on the situation, but generally. And I'm doing research in something called quantum federated learning, or how can we use quantum computing in these setups. And there's a bunch of different ways in which you can do that. You can establish quantum communications. You can have a quantum model. We're using variational quantum circuits. And we publish this state-of-the-art also, if you're interested. And currently, what we are doing in the actual quantum computer is to use this federated setup to tackle a quantum information problem, which is quantum state discrimination, in which you have to basically classify unknown quantum states. And these two plots are from a simulation, and we got accepted really recently, like last week, a paper into Ekai's workshop, so the results were promising. And the plot in the right are you can see the actual quantum experiments, and we have seen that this federated setup really helps learning, even in NISQ devices. And that's all. I'm more than open to discuss quantum things with you, and of course open to possible collaborations if you want. And thank you for listening.
Thank you, Rocco. Is there any question for him? No? Okay. So let's hear to Andoni Alou from PIC speaking about machine learning techniques for improving quantum optimal control for some superconducting qubits. So when you're ready.
So hello everyone, my name is Andoni, and I'm going to talk about this work that we are doing in the last REST call about trying to use machine learning to improve the control and the gate fidelity on superconducting qubits. So first of all, who am I? I am a PhD student. I work both as a collaboration between PIC and JIC. JIC is the group of quantum information theory at UAB, and PIC is a data center that's part of the REST, which is also in UAB, and I leverage both machine learning and data science techniques with problems in quantum information and quantum computation. So the problem that interests me is the problem of quantum control. So a good way to understand this problem is thinking about classical control. So the problem of classical control is you have a system and you can control some parameters. For example, if you want to heat a room, and you can control the intensity of the heating apparatus. So for example, if you want to accomplish some goal, for example, keeping the room at a constant temperature, then you would need to find the optimal way to change the temperature of the heating apparatus, so you waste the least amount of energy and you can maintain the room at the same temperature. And there are nice analytical solutions for this, and you can think of this problem in the quantum sense. Now you are in a much more difficult scenario because your system is much smaller and is more difficult to treat, but what you can control is, for example, in a superconducting qubit, you will have a part of your Hamiltonian that will depend on a microwave pulse that you send. And you can try to optimize these microwave pulses in order to achieve for example, here I'm trying to do a classic quantum gate, and you could try to find pulses that improve the time that you need to implement this gate. For example, you can find shorter pulses than the ones used usually used for this device. And you can use machine learning to try to learn these new families of pulses for your concrete device. The problem is that while you can have an analytic description of your system, this description is probably going to be wrong because your system can have defects or can have interactions with the outside world, and you will probably have terms on your Hamiltonian that you cannot account for. So what you can use is a very nice technique from classical machine learning, which is called neural differential equations. This uses the property that a neural network is a universal approximation for any function, and you can use the neural network to model the terms of your differential equations. And there is a trick called the adjoint method that allows you to compute your gradients of your loss function efficiently, only doing a forward pass on solving your differential equation, and a backward pass, which will solve the differential equation backwards in time. So this is computationally efficient. So what we do is we use these neural differential equations to model the unaccounted terms on our Hamiltonian and try to improve and then use this to train our new pulses. So the complete framework would be, we have a initial guess for our Hamiltonian, which is perfect Hamiltonian. We compute a family of pulses that compute all of the rotations around the x-axis. We implement them on the quantum computer. We get measurement data from these, and we can check first if the pulses are doing okay, and then we can use this measurement data to train our neural differential equation. Then we implement this neural differential equation in our model, and we train again our pulses, and we get a new family, and we put it back in the computer, and we train again. We haven't implemented this, so we don't know if this is going to take 10 epochs or maybe 1,000 times this process, but we hope that it will lead nice results. And also for current needs and future needs for quantum resources, well, two of them also Raúl already tackled them before, so the problem, but I would like to have like a detailed model of the quantum computer that we have today in the Quantum Spain project or in QMI, and maybe some parameter estimation of the different parameters of this Hamiltonian beyond the ones that you do to try to calibrate the pulses. And that's all. Thank you for your attention.
Thank you, Andoni. Andrés has a question.
Thank you very much. It's a very nice work. I hope that you have a solution. A couple of questions, very fast question, because you are asking for a Hamiltonian of the system. A Hamiltonian of our system with 32 qubits plus the 32 resonators back connections maybe is impossible to model easily. So yes. I wonder about if you are looking for a Hamiltonian for a single qubit plus a resonator for a set of qubits.
So for example, maybe like a local Hamiltonian for each qubit, which will model like the Hamiltonian, so the frequency between the levels, the leakage, and probably the like constant interaction between the nearest qubit neighbors. That would be nice enough.
Okay, thank you.
Anyone? Yeah, there is another question in the fourth row.
Hello. And talking about the number of gates that you want to parameterize or better implement, are you thinking on just tackling like the separable basis gates of the system, or are you thinking also on applying more than one gate at a time, or also taking these like, I don't know if you are aware of these gate set models where you are not taking into account that just one applying the same gate into different qubits are actually different gates?
So our plan was first start with easy, so the 1 qubit gate, then try to do 2 qubit gates, and then maybe try to optimize like unitaries that you might use. For example, try to optimize a unitary that does a bell state or something like that. This was a little bit our plan. for the different steps, but we are now first making the 1 qubit gate work.
Okay, thank you.
Okay, if there are no more questions, no? Well, so the last presentation on this topic is, and to close this roundtable, is about quantum advanced real-time car body optimization with Fabiola Cavalier from SEAT. Sorry.
Thank you. Okay. So first of all, thank you for inviting me. I feel a little bit like an outsider, I have to say, because to be really honest, I don't know a lot about quantum computing. I'm from SEAT. Let's say the story behind is that we were contacted by Barcelona Supercomputing Center. We were proposed to make some kind of projects together, and we came out with some of our typical industrial problems, and we jumped into this new adventure. Hopefully, will bring some first steps or nice first results. So I won't tell you any quantum, let's say, approach, but I will tell you the idea we proposed, and we should start very soon, because also we have some bureaucracy problems due to the big companies sometimes make it a little bit more difficult. But anyway, so just to give you an idea of the context where I come from, I'm from the functional simulation department at SEAT. This is where we basically run virtual tests, simulations, numerical simulations about the main functions of the cars. So we have 3 subgroups, one mainly about aerodynamics and related stuff, another one about stiffness, crash acoustics, which is the field where I work, and I try to apply artificial intelligence to this kind of simulations. And then we also have occupant safety and everything related to interior trim. But just to give you an idea, so where I come from, let's say. And as I said, I'm trying to apply artificial intelligence to the development process. At the moment, we have 3 main technologies that we try to test along the whole process, starting from the design concept, going to the concept definition, the development itself, and the final project validation. Some of them are, let's say, built from SEAT, through PhD projects, actually. One of them was mine. ARCO comes from my PhD in collaboration with SEAT. And this is just to tell you that, I mean, at least the company is really involved into this bridge between academy and industry. And that's why we wanted to jump on this project as well. Anyway, just to give you an idea of the specific problem, one of them that we every day try to solve. This is a typical test that we need to assess. It's called the NVH analysis. This means noise, vibration, and harshness. This is basically a target that we need to fulfill because it's really very well related to the comfort of the passengers in the car, so in terms of acoustics, vibrations, and of course every change in the structure of the car affects these targets. And it's kind of not so easy. It requires a lot of iterations in order to be fulfilled, not being conflictive with other targets at the same time, right? And at the very end, what we solve in the preliminary analysis is a static stiffness problem, which is basically to solve a linear system of equations, basically. And the other part is a modal analysis, a dynamic stiffness of our car, which means finding how the car vibrates, see at which frequency some specific modes appears, like the first torsional mode of the car. So this is basically solving a generalized eigenvalue problem. This is what's behind. And how do we do it? Iteratively. This is the classical trial and error. So we need to run many times the same simulation by changing some structure configuration. And we can understand which are all the limitations, right? It's very repetitive. You have spare data. Sometimes you lack to recognize some patterns in the behavior, and somehow it's limited by time, by cost. So at the very end, we need now to be very fast in the development process. The world is very competitive in the automotive, especially at the moment. And that's why we thought, okay, the best here would be if instead of running every time a new simulation where we change some parameters, we were able to directly build a parametric modeling. What do I mean? Like, for example, let's keep these 3 car components. Of course, we have a lot of car components which can have parameters, but let's say these 3, and we want to play with the thicknesses. This has a big impact on the stiffness of our structure. And let's say that or cross-sections, geometries, whatever, and we say that we know ranges due to, let's say, from the manufacturing point of view, costs, whatever. You can imagine that as light is the car, the best, but of course, keeping some kind of stiffness properties. So let's say that would be ideal if we were able to model our structures in a parametric way. But the problem is that, let's say that we have 1 parameter which can take 10 values. Okay, we have already 10 configurations. With 2 parameters, we will have exponentially 100 configurations. I don't have to tell you, if we have 10 parameters, we have already 10 billion configurations, which with standard numerical methods, it's not feasible. We are in a very high dimensional problem. Every simulation takes a lot of time, computational costs, and all this stuff. So what we started exploring was the other very trendy topic at the moment, which is machine learning, specifically dimensionality reduction. So the idea is like with pictures, right? Maybe I don't need to see that this is a landscape with a lake and all the details, but I can already see in a reduced format, like when we compress pictures, I can understand it's a landscape at least and not a dog or a cat. So basing on this, this idea, we developed ARCO, which means Advanced Real-Time Car Body Optimization, which is a machine learning-based methodologies. It parameterized, in few words, let's say we have 3 steps, a pre-processed data where we basically parameterize our model according to the engineer's suggestions. We sample, let's say, the input data of our problem that at the very end are 2 matrices. One matrix, which is the stiffness matrix that has all the information about the geometry, the material properties of the car, and the mass matrix, which is basically, the mass of the car, but in this finite element. I don't know if you're familiar with that, but we solved this numerical problem. And then we apply a specific dimensionality reduction method, which is called proper generalized decomposition. And it's basically having a lot of algebraic operations, divisions, additions, linear solver, and things like that, that can be solved now in a parametric way, instead of, let's say, single configuration. And then we have a post-process part where we basically have a function of our results that we can explore in real time, as it is typical in machine learning, having in mind some kind of optimization problem, right? Because at the very end, we want the best performance of the car with the minimum costs or weight of our cars. So this was the idea we proposed to our colleagues from the BSc, and the question was, can we bring this idea to quantum computing? So we are basically now starting this collaboration. My feeling, especially, so today here, I want to learn a lot from you. Actually, sometimes I get lost, but at the same time, I'm getting some hints. Many things which are interesting for us were mentioned, optimization problem, also the federate learning and all this stuff. And so, let's see how can we start from a very simple problem, most probably. We won't start from this kind of large problem, most probably. But please feel free also in some break to give me any suggestions. I will be happy to hear about it.
Thank you, Fabiola, for sharing with us. Is there any question? Yeah.
Thank you for the presentation. It's very interesting. Actually, I was thinking to do something similar, but not in cars.
Yeah.
What kind of differential equations are you solving for this system, or you're not solving nothing?
Yeah, this is PDE. Like, I mean, at the very end, we are going from partial differential equations to the classical algebraic representation to be solved in this finite element framework.
It's like, I will use a very fancy word, but it's Newtonian mechanics or not?
Yeah, at the end, that's it. And I mean, the matrices and so on also have very specific properties. They are
constraints and many things.
Yeah, and they are symmetric, positive, definite, all this stuff, which I don't know if it's something you were also interested in, but I personally have a lot of questions about it. I don't know how this kind of problem can today be solved through quantum computing. I guess it's already a good start if there's a way to translate a little bit the mathematics behind. I think Antonio, I think was the name, at the very beginning was making my mind clear in that sense that if we don't have the mathematical clear expression of certain problems, of course it's maybe the first starting point, but again, cannot help a lot at the moment.
Thank you.
Yeah.
Thank you.
Okay, there is another question.
Yes. Yeah. Correct.
Is there any other question for her? No? So just to close this topic, I would like to ask you your opinion about how far do you think we are from in quantum machine learning to be competitive with the classical one, with machine learning, if it is not?
In my experience, I'm talking about optimization and this kind maybe of industrial problems. We are really far away.
Okay.
And when I approach this optimization stuff, like the TSP or SAT, I'm trying more to benchmark the quantum model more than comparing myself to the classical solution, because we're gonna get like really beaten up.
Okay.
That's my experience.
Yes, I think that if we think about quantum machine learning as trying to beat classical machine learning, it's a race that we are not never going to win. We can think of different problems that maybe machine learning cannot tackle, but we are not going to work better than a GPU with a large language model.
So, okay, thank you, the fourth of you, because of sharing your projects with us. They are being really interesting. So let's continue with the session.
We have Raúl Ignacio Guerrero Aviles from Tecnalia, and he will talk about chemical systems on small quantum computers.
Thank you. Thank you. First, I would like to thank the organization for the invitation for give you all this talk. The original title of my work was Chemical System on Small Quantum Computers, because the main idea was to test all the simulations in the MareNostrum-Ona quantum computer, but I have to change it a little bit for a small system on small quantum computers, because I have to migrate from one system that I had in mind to another systems that actually Raúl Fuentes was the one that helped me a lot to move on to this new approach. The system that I had in mind at the beginning, it was a very simple system that is led by this Hamiltonian over here in the top right side, which is essentially to simulate systems that you can find in tritium. Why tritium? Tritium appears in nuclear fusion reactions. So the main idea is to obtain via a VQE algorithm the ground state energy of a tritium system, and also then by VQD algorithm go to higher energies like the excitation of those of the main ground state that you can find in the theory. The first approach is essentially not deal with the VQD, because VQD needs to be done by first a very good Polish VQE algorithm. But the main problem that I face here is just I cannot yet apply it in the MareNostrum-Ona. Because why? Because essentially here is the model, but I'm using Kivo for 4 qubits, so it's helpful to use it here in the MareNostrum-Ona, and I think this is the blue one, because Raúl was telling us at the beginning in the morning, sorry, in the afternoon, that the blue one is the operative one, right? Well, on the right side, the left side, you can see here that the classical or exact simulation works well, but I have the problem still with how to implement this system to the MareNostrum-Ona. I mean, at least the script that we discussed at the beginning. So I migrate to the script that Raúl gave me. On the first test, I performed like around 15 tests. It's not enough, but it's at least gives me one idea that what we can do with MareNostrum-Ona for a simple system of Ising model. Ising model is it works very well as a use case for new quantum computers. Even we have improved in D-Wave, in the ones from IBM and so on. And the results are not so inspiring, essentially, because as you can see here, we cannot see any trend or neither a physical conclusion of the results. Here you are watching the energies and the different iterations. So why 6 iterations is because the wall time. The wall time is not enough even for this kind of simple system to simulate. And I will suggest first, next slide, is what we need now from the technical support of MareNostrum-Ona is first of all genetic libraries to test the state-of-the-art algorithms in this kind of quantum computers. That will be very helpful because we don't want to deal with the coding of these kind of things, because we want to do research for this system, not the coding of this kind of to deal with the quantum computer. Also, somebody tell us in one of the talks that it will be very helpful to have a backend simulator to debug our codes and not send the quantum simulations with a code that is failing in some part of the lines. For example, the ones QEmulators was I forgot you are using fake backends in a way, so that is very helpful because in a way we don't want to use a very expensive machine just to not spend money. Also, well, as I told you before, increase the wall time. That's good. I know now by Raúl that is we just need to send an email.
But again, I would like to insist more strongly in the thing about the community. The community, I think, is very important because, again, I had experience already that when no matter the size of their community, if you are 3 people and you are dealing 3 people with the same problems, it will be helpful to overpass that problem. And well, nothing more to show today, but thank you for your attention.
Thank you, Raúl. So now we will go to Alberto López Garcia. He will present modeling. He's from University Polytechnica of Cartagena, and he will present modeling impurity noise in NB centers via quantum computers.
Okay. Hello, everyone. My name is Alberto López, a PhD from the Technical University of Cartagena. And our topic is about modeling impurity noise in MB center via quantum computers. Those are some of the topics covered by our group, also the members and the funding that support us. Okay, first of all, what is quantum sensing? Quantum sensing is like the use of quantum phenomena like superposition and entanglement to detect extremely precise measurement, for example, electric and magnetic fields. And on the other hand, the MB center is a point defect in the diamond where a nitrogen atom replaces 2 adjacent carbon atoms, creating an electronic spin 1 that can be precisely manipulable by using microwave and laser radiation. And all of this make it highly suitable for precise advanced sensing applications, such as nanoscale nuclear magnetic resonance, magnetometry, and so on. So the purpose of this research is to analyze the effect of spins in the vicinity of MB centers, where the main goal is to create entanglement. So our case is formed by a 2-qubit system, which is characterized by 2 MB centers. That is, qubit 0 is an MB center, and qubit 1 is another MB centers. And furthermore, we have analyzed all the different scenarios. For example, we have analyzed the effect of a carbon-13 in the vicinity of, or in the coherence of an MB centers. But for today's presentation, this is our setup. So considering the MB center interaction, those are the sequence applied to each one, to the qubit, and therefore to the MB centers. To an echo sequence with different initialization states, state plus for the qubit 0 and state minus for the qubit 1. And at the end of the sequence, we have applied quantum state tomography to measure in different bases to have the full spectrum in order to analyze the data. Once we have collected the data, we have performed different analyses. The first one is related to the purity of state. We start with the data measured in different bases. Thanks to the quantum state tomography, we construct the density matrix, and then the purity of the individual state and the mixed state. If the purity of the mixed state is greater than the product of individual purities, it is a sign of possible entanglement, which is exactly what we observe here in our results. The second one is related to the Perez-Holodecky criterion. We start again with the quantum state tomography. We construct a modified density matrix, not a normal density matrix, a modified density matrix by this criterion, and then we obtain the eigenvalues. In this case, negative eigenvalues by this criterion, I mean modified density matrix, because in a normal density matrix it is not possible to have negative eigenvalues. So negative eigenvalues by this criterion means entanglement, which is exactly what we observe here in the evolution of the eigenvalues by this criterion. And the last one is related to the CHS inequalities. We start again with the quantum tomography, we construct the density matrix, and by a specific analytical equation, we obtain a correlation parameter. In this case, values of this correlation value greater than the absolute value of 2 means entanglement. As can be observed, in this case, it doesn't reach that threshold, meaning that despite we have entanglement, because we have observed in the previous one, the entanglement is not strong enough. And now the theoretical analysis. I will not go into great detail because of time, but we have obtained the evolution of the theoretical value of the state. At first, we have the state plus minus because it's the initial state. We have initialized the state to the plus minus. Then we have entangled state, minus plus, entangled state, plus minus again, and so on. Well, If we compare the result of the evolution of the eigenvalues with the theoretical prediction, we can observe how they fit perfectly, correlating the theory and the experiment. The other hand, regarding to the need from BSc, I have also some emails with Raúl. We need necessary to have pulse control, because in this way we have access to the qubit physics, we can design advanced sequence, precisely calibrate the rotation, and therefore we can characterize the system. But most importantly, we can treat the MB center as a 3-level system, as a Q-treat, instead of a 2-level system, a qubit. And this is only possible by pulse control, because our idea is to use the next transmode level, that is Q-treat or QDIT, to have an analogous scheme between the MB center and the quantum computer. So the MB center scheme in the quantum computer, because it's a Q-treat. Also, we have a recent paper related to the use and control of MB center as a 3-level system instead of a 2-level system. Sorry. So in conclusion, we have observed entanglement in the interaction MB center, but it is not strong enough because we have a low fidelity because of the non-violation of the CHS inequalities. However, we have observed correlation between the theoretical prediction and the experimental outcomes. And from now, what we need from BSc is pulse control to have access to the qubit physics and characterize the system, but especially to have a 3-level system. And the future research along with BSc is to improve the entanglement fidelity, surpassing the CHS inequalities, and test new sequences and scenarios, and also try make experiment with the idea of the 3-level system that I have explained. And that's all. Thank you for your attention.
Thank you, Alberto. For this session, we will keep the questions for the last because we are a bit out of time. But now we have the next speaker, which is Silvia Riera from Universidad Autónoma de Madrid.
Thank you. Hi, everyone. I'm Silvia Riera. I'm a PhD student at the chemistry department in the Universidad Autónoma de Madrid, supervised by Jesús González and Alicia Palacios. And well, in this presentation, I'm going to explain you our 3 main lines of work regarding quantum chemistry in quantum computers. Okay, so our first line of work focused on simulating non-adiabatic molecular dynamics with quantum computers. The ultra-fast electron dynamics are very important to study any type of processes that includes light interaction. However, because of the many electronica and nuclear degrees of freedom with classical computers, often we need to reduce the active space of the molecules we want to study. That is why, in this first project, we propose a scheme that uses classical techniques to simulate non-adiabatic molecular dynamics with quantum algorithms, with the aim to simulate bigger active spaces. During the first project, we realized that it's not always easy to represent all types of excitation between our electronic states with one ansatz, or in our case, with one parametrized quantum circuit. That is why we dedicate our second project to create good initial states that are going to be cost efficient and are going to be useful for any type of bond type or molecular geometry of the system that we want to study. And finally, well, this is the third project we just started. We wanted to move away a little bit from the variational algorithm philosophy. We wanted to try something that is going to be very challenging, but we are very excited about it. So yeah, so we just started, so I can't tell you much of how it's going, but well. Okay, so I'm gonna go very fast with the first project. Well, the molecular dynamic technique that we use is called surface hopping, okay? Which very, very simply, what it does, it follows the jump of our dynamic along our trajectory. And well, we changed the part that are going to be, well, are right now challenging in classical computers, that are the colored part, with quantum algorithms. I'm not going to go very much into detail, but if someone is interested, like, we can talk during the conference. These are the results. We use the, well, IBM simulators, but we are working right now, we are trying to simulate the, well, to run this in the blue chip, in the BCC. It's a work in progress. It's going to take a little bit of time, so I don't have results right now, but we are very excited to see what comes afterwards. Well, the plots over here just shows you the dynamics that our molecule, our test case, the methylamine molecule, which is the one that you can see plotted over there, follows. You can see how if we start from an excited state, then we change to the grounded state and the change of geometry occurs. So finally, well, first of all, I agree with all current and future needs of quantum resources that Raúl actually mentioned. We were more or less using the same algorithm, so I totally agree. Well, for the first project, we have hopes to simulate that in the BCC QPU, because, well, the number of qubits is actually low. However, the depth or the number of gates is not nothing, let's say like that. So we are not sure how we are going to manage this, but for sure we are going to try, and at least we hope to have some points. Maybe not the whole dynamic, but at least some points in order to compare. With the second project, the number of qubits is a bit higher. However, an interesting point here would be to be able to parallelize the quantum circuits, because we don't need one result in order to run the other for the complete results, no? So that would be very interesting. And finally, for our last project, the grid methods, I'm not sure if we are gonna, like, at least during my thesis time, being able to simulate that into a quantum computer. But right now, well, this morning I heard about the emulators, and I'm also, I mean, for the next call, for sure I'm gonna ask time in there, because I'm also excited to see if, at least for a very, very small test case, because the number of qubits that I'm writing over here are for test case. This is the minimum amount that we can have to have something that is meaningful enough, but not, I mean, it's not very like real case, let's say like that. So thank you very much. If you have one question, no, but thank you.
Actually, now there's time for questions. So please.
Okay. I have one question for Raúl. Yeah. So in the VQD that you plotted over there, you said like maximum you could do 5 iterations, or in the VQE. With the VQE. How many parameters did your circuit have?
It was 5 parameters,
okay.
Something like that, yeah.
Okay, okay.
It was a very small system, yeah. 5 or 6, but it's not changing much.
Is there any other question here? If not, I have a question. How far is it this field to have a practical advantage with the classical methods?
Who want to start?
I'm just going to say something that I think is going to respond that. Like when we do this, like my supervisors are like quantum chemists, like theoretical chemists, and every time we achieve to do something, they kind of laugh because it's so easy to do it with the classical computers, and with the quantum computers, everything is so, like a lot of gates, a lot of dead, a lot of qubits, and they say like, we spent 1 month to do this. But, so yeah, like I think it's pretty far.
In the sense of computing resources, will be this maybe some advantage of it? Because I know chemical simulations can consume a lot of hardware time, right? So,
yeah. Maybe you
yeah. Well, it's in the same line. We are like also thinking that is very far away, but there is hope in the sense that you cannot measure quantum computing against DFT codes or classical methods. I mean, conventional methods. I don't like to use the word classical. Because conventional methods has a lot of years of development, and they are really tuned very well, the screws. But quantum computing is I define it as we are in the stage of, or I mean, the people who develop quantum computing are in the stage of, I don't know how to say it in English, but the tarjetas perforadas. We are specifying to the to the QPU where to compute that qubit in topology of the QPU. Is not fair enough to compete with that. And on the other side, there is for quantum chemistry, quantum computing is having some results, but it cannot compete with a system like with the DFT. But in the other sense that there is another kind of models like a SSH model and other more physical inspired models where the quantum computing can bring a very new, open a very big door, let's say, because for example, when you go to these topological models like SSH, as far as I know, you can go about 20 orbitals or 20 sites. So when you go to compute that in a classical computer, it will not calculate at all. So then you have to go to a quantum computer. And in a quantum computer, myself, I have calculated things in, I don't know, 60 qubits. And when you go back to the runtime, at least in the IBM quantum computers, each step is 40 seconds. So it's quite nothing for 50, 80 qubits.
Question for Andrés?
Well, it's more a comment than a question, because it's important what you said. In some computers, you cannot calculate many things, as you said, that we can calculate classically. That's true. Okay, but one of the possible quantum advantages is when or how much time do you need to calculate the same things. Because when you increase the size of the problem due to the way that the quantum computers works, you can do things faster than classically. not for small systems, which is qubits or 7 qubits. Maybe we can solve the problem in a laptop without problem in less than 1 second. But when you increase the size of the system, usually there, for example, DFT, I don't remember exactly, but I think that it increased like number of orbitals to the 7 or something like that. I don't remember exactly that. So it's very, very important. So the problem is when you increase the size, maybe the quantum computers will solve the problem faster. I agree that the problem is that the high-level APIs are not ready yet, but there are some ones. For example, do you know Open Fermion?
Yeah.
Okay. Open Fermion.
So, yeah.
Open Fermion, you said. Oh.
Yeah. In this case, you work at high level, okay? And we have to transfer the problem directly to the circuits. Has no sense at all to work in your field or other fields with gates, because it's like programming an assembler. That is it's not a good idea at this moment.
Also in the same line of that, quantum computers, if you compare with DFT, DFT is a theory that is in the frame of mean field theory, right? But in physics, at least, we want to go further to many body systems. And SSH, for example, is a many body system. Hubbard model is a many body system, and so on. Those models still in the literature is small, but when you go to a quantum computer, there is much more hope to calculate the things.
Okay, are there any other questions? No? If not, just let's add it as one.
In the case of DFT or Hartree-Fock method your problem, you solve the problem numerically. That means you take the equation and solve the equation.
Exactly.
But in the quantum computer, it's a little bit different, because when the qubit run, you are solving some kind of a Redinger equation, but it's not the Redinger equation numerically. It's the physical system that represents the Redinger equation. So it's a little bit different, because I think that for me, quantum supremacy is a hoax, because there are no sense, because you have two devices that are measured in a different computational units. Okay? So I think that for me the question is how kind of problems are useful to be solved with a quantum computer, because are totally different with classical ones. I think.
Yeah, can I say one last thing? Yeah, like quantum chemists are very sorry, I don't know how to say it in English, empeñados? Yeah, obstinated on replicating the classical method that we're developing for quantum chemistry in quantum computers, like you say, Hartree-Fock on a quantum computer, CASI, multi-configuration, everything on the quantum computers. So yeah.
There are nothing to do, because all these methods are based in the variational principle of Dirac-Frenkel, which is performed in a classical one, because you reduce your space in order to
exactly.
use the finite element method in an intelligent way.
Exactly. That's why I said we were so excited about the third one, because we are going to try to change a little bit the mindset.
Indeed, I explained you. The method used by SEAT, the PGD, is based in the same, with the same principle, which to perform in a classical computer is totally optimized. Indeed, if you use, for example, TensorFlow or something library in Python, as this library, or use TPU or GPUs, the geometry of this hardware is adapted to this kind of operation. So it's more easy to solve with this kind of machines.
Actually, myself, I have been doing I don't know if somebody is related with the SQD algorithm. It's sample-based quantum diagonalization. The IBM developed a nice paper last year, at the very end of last year. I have been working since then in that algorithm. And SQD is not variational, but it uses a variational circuit. So you first, with with Monte Carlo, you optimize the circuit of the ansatz, then you go, you sample. You don't use the estimator, for example, in the case of IBM. And yeah, you get a lot of samples. Some QPUs don't give you nothing because it's just noise. But right now, I'm finding some, after 3 million of sampling, I'm getting the counts, that is the bit strings that are the same. And now with the R2 Aeron chips of IBM, I expect better results even. And another thing that I would like to say that at least the SQD algorithm is a new perspective because you are not making variational things, so you are not interacting each shot or each job with the classical computer. You just send some shots. And in a way, your answer is spanning Hilbert set more smaller. So because you give classical information, at least with PySCF, actually, I'm using PySCF, to feed that algorithms. So it's a new way to deal with this problem, because VQE, at least, is in the near future, it will be very hard to find something with variational algorithms. So almost impossible, because actually, for hydrogen molecule, last year with IBM computers, it was taking more than a week for a bad convergence. But with this QD, you can do it in, I don't remember what, for benzene molecule was at least, 3 hours, I would say, but it was much more or less than half of a day.
Okay, so let's thank the speakers. Thank you very much for your nice talks and discussions. So now we will have our next roundtable. That is Applied Quantum Computing and Software Engineer. Could Laura, Marco, and Enrique go on the back for the micro? From University of Barcelona. She will talk about pilot tests of quantum algorithms for market segmentation and consumer behavior prediction.
Okay, good afternoon. Thank you very much. I am Laura, and I will present together with my colleague Jorge Favilla. We are an interdisciplinary team. We are from marketing, from business economy, and we work together with computer science, maths, and physics. So it's a real case of we apply this, and we have tested in ONA, Barcelona Supercomputing Center. I want to thank you to Raúl for the support, because without him, this project will not be possible. Dr. Santiago Forgas, Dr. Carlos Martín Islan, Dr. Karim Lekadir are part of this project, and more researchers. Okay, this is a pilot. Really, what we want to do is to test if we can present a full proposal for 5 years with quantum computing. It's just a test, and I advance you that we are satisfied with the results. Okay? We were skeptic, but at the end, we have I don't know how to say it, but we have better results than what we expected. But be conservative because it's just only a test. Okay, here, as we are in the last part of these sessions, there have been explained a lot of concepts like feather learning. We use data from feather learning. It has appeared also other types of concepts like salesman problem. I don't know how you know about marketing, because this talks about marketing. Salesman problem, it's a part of marketing, one of the parts. So what we want to solve is to cluster market and cluster consumers. Why? Because machine learning and all the types that we have used, of course, my colleague says, okay, when we take something with quantum, we nearly love, but yeah, I agree, totally agree. But with machine learning, what we cannot get is outliers. And with quantum, besides we are like, my colleague says, we are like, I remember the targets with spots. I remember this, and I remember about computing with 64 keys when I was 6 years old. So now I am with this enthusiastic for this. So what we want to do is consumer behavior, clustering, and know these different types of problems. We are not trying to solve classical problems. We are trying to solve different types of problems that cannot be solved with classical machine learning, deep learning, all of types of this. And we don't think that we can resolve, at least in 5–10 years, but we can optimize, because the problem cannot be solved with classical 0–1. Okay, these are projects that I am the PI of this, all based in machine learning, feather learning, data preparation, data clustering. Now I am in the user because I am trying to look for distance, but okay, I'm not happy enough. I need more. I need more. And I think that quantum can solve. Last Friday, I was having lunch in the physics faculty and saying me, one colleague in the line tell me, okay, have you visited Ona supercomputer? And I said, yes. Do you know that 31 researchers are full and are trying something? And I say, yeah, I am one of these fools. So I know that perhaps I am a dreamer, but I believe in this dream. I'm not sure that it's a little bit hype, probably yes, but it's investing some money and investing sometimes on, we are doing things, so probably at the end, something will reach. I don't know the results, but probably something. So what we are looking with Jorge and with all the researchers is to, at least, it's our goal, have 10% improvement on classic basic lines in segmentation accuracy, processing time, pattern discoveries, scalability, and noisy data handling that with machine learning I have some problems. So we have doing this in Ona with their support. I am very happy with the support of Barcelona Supercomputing Center. We have pre-processed the data. I am collecting data since 2010. I have more than 7 million of users in Spain. Pre-proceed, but for this we are getting the synergies with the Federate and other projects. We are using data from persons that could have chronic heart failures, that we know a lot about this database, and we can make a very good benchmark. With this, we have launched a lot of pipelines that my colleague Jorge, the technician part, will explain you more, and we can explain you a little bit our experience. So this is our frameworks. You know, in Barcelona Supercomputing Centers, they use these frameworks, not the classicals of IBM like this. And all of this, we expect this scalability. Of course, it's 4-month project. What we have not finished. We have applied it for the second period. We expect we get the hours because we want to follow with this. If not, okay, perhaps we finish our 5 years project, but we expect no. And okay, this is the technical key parameters that we have used. More or less how we estimate the distribution of computational resources, okay? And I pass my micro, the floor is you, Jorge, and then I come back for explain the real experiment that probably we will publish soon.
Well, so basically this is a pilot study that we designed in order to basically to get familiar with the infrastructure and to know the difference with the theory, the tutorials that you can find in the internet, and how different it is with the reality, no? Because we just realized that it's very different. And we tried, since we are a group of research in artificial intelligence applied to medicine. So I'm working in this project that is AI for heart failure. And we're familiar with some machine learning cardiology data sets. So we decided to use these data sets and some basic models in order to use them as baselines. So in this plot, you can see the different set of algorithms. In blue, you can see the classical support vector machines. In green, you can see the quantum support vector machines, but the simulated one. And in red, orange, and yellow, you can see the actual performance. So you can see that the difference between all of them is basically nothing, no? So we're not basically gaining anything from the quantum algorithms at this point. It's true that it's a very naive algorithm. And if we compare the performance in time, you can see that the actual hardware gives around 1,000 to even 100,000 times slower, no? So this is very interesting because, and somebody was asking before how far are we from the machine learning with quantum machines, with the classical, no, with the CPU machines, and we can say from this that we are quite far, no. So we also try to look at the performance of the machine, and this is very interesting because the way you can use the code in the tutorials is very different to the actual machine. So we can hear the performance of based on the number of qubits and the number of shots, no? So the number of measurements that the machine is taking, and you can see that this is scaling as we could expect, no? We increase the number of qubits, it takes a little bit more time, but something very important is that it takes some time to prepare the instruments, and this is something that you don't realize when you look into the tutorials, no? There are a lot of papers and many research, a lot of hype about the machine learning in quantum machines, and maybe they don't take into account the actual electronics and the things that is actually happening behind, no? So I'm going to pass this very fast. So this is the more results about how is the performance of these models. And this is a very interesting other model that is quantum inspired, not exactly used with the quantum machine because it took a lot of time, because it's taking profit of the orthonormality of the states once the data is coded into the machine. So you can see that in this time we are actually outperforming the classical, no? But it's not tested in the real machine because it takes a lot of time and the limit is 10 minutes. So we didn't have time for testing. It takes 10 minutes the maximum, so this was also a very interesting limitation. So this pilot is to get familiar with the infrastructure, to know what we can do, what we cannot do, and to set up everything based on this project, because we wanted to take profit of then the traveling salesman algorithm. But first we have to start with something. So that's why we start with this project. So this is our next steps. We would like to have to develop some more algorithms. This is a very interesting figure from one paper that is the algorithm that I showed you here in purple, that is taking profit of the orthonormality, of the states. So the vectors that are similar, they're clustered together in the Hilbert space, and this is the representation of these states. So, well, this is the pilot, and back to Laura.
Okay. One of the things that Jorge has, for me, for marketing, as an expert in this, is the recall. The recall, for me, it's very important with this because this has implications directly to the market. Okay, if we make this recall, imagine a call center or like this, you can have a big amount of consumers that could be interested in this. So this has implications in, of course in science, but in the real life could have implication if this, when we scale this in big data, because it's the test, could have, it's an index that could have implications because for the false positive, not the false negative. So it's better for medicine, it's better for a call center, it's better for, it just 4 months test. But when we have this, we celebrate. It was not a love that joking, it was, the first index that we can have results. So for this, we are animated to prepare the feasibility that we can prepare this proposal that it was in my dream a lot of years and now. So, because I don't want to extend more, this could have implication. This is our, it's not a GAN, but it's the project timeline. And the current need, because it was requested to ask, it's just a dream letter, of course. We accept anything that could go, of course, more qubits. It could be perfect because, but we remember the classical computing, the starting, so I am positive, I have an age, I am not so young, I am happy to see this kind of young people here motivated with this, but I remember the starting of classical computing. I was lucky because I could have it, I could have access. So if we can have more qubits, it will be very nice. And GPU basic classical simulators for algorithm prevalidation, it will be perfect. And every classical quantum runtime for optimizations models also having support. And near future needs, you have here, but it's because we have been requested. Our main is say thank you. So thank you everybody for listening, and no more other questions.
Thank you very much, Laura. So as in the last session, we will keep the questions for the last minute. And so now we have Marco Miguel Aguado from CETIC, who will present applied use case of quantum computing in the context of ARQA.
No, it's okay. No, era esa. Okay. Can you hear me well? Okay. Well, first, thanks to your organization for inviting us to this event. It's quite interesting that we started from what tools do you have, that here in Spain with the quantum computers and simulators, then from the mathematical basis of all of this that we are talking today, then to some use cases or some cases where we can apply this, and then all the quantum circuits and fundamentals start to disappear, and we come to the like use cases. So what can we do with all the things that we've been talking today? So first I will give a very brief introduction to us. I'm Marco Miguel Aguado. I'm a technician and researcher from CTIC, which is a very small research center in Asturias, north of Spain. And we started this career in quantum computing in 2018 with the development of Qt emulator. At that time, there were not many works in this area, so it was a very brave jump at that stage. But during these 2 years, we managed to finally establish the simulator and test how many qubits we could emulate with the hardware that we had. And currently, we can emulate around 30 qubits, something like that, logical qubits. Then when we finished this process, we said, okay, now we want to see where can we apply this. We have to start investigating, researching which use cases could be interesting, and that's when we started the Alcatraz project. And I know the name sounds a little bit weird for a quantum project, but here in this project we tested 3 different use cases for that were classification, so using QML, optimization, so quantum optimization, and quantum simulation. For the classification, we try to kind of detect kind of network attacks. We had network information about the behavior of different servers in a network, and we try to detect which of these interactions were evil or could be dangerous. Then for the optimization, we used some of the data that we used in previous work, because we do a lot of work with companies there in Asturias related to optimization of routes for logistics and distribution. So we use some of the data to try to optimize these routes with quantum computing. And as you know, the size of the problem has to be reduced a lot to kind of get a real solution. And finally, with the simulation, we have a collaboration with the Universidad of Oviedo, who helped us a lot in that regard. Then when we finished this first approach, we kind of got some conclusions about what quantum computing could do, and it wasn't much at the time. But we said, okay, now we want to give another step, make it a bigger project, and that's when ARCA, we started the ARCA project, which is actually a national network that we try to not only develop or try to develop real use cases, but also show this technology to companies and other researchers. So let them know that this technology exists and it has a lot of potential for the future or far future, depending on the advances in hardware quantum computers. And we collaborated with 2 partners, Eurecat from Catalonia and ITG from Galicia, and then also us. And now I want to present the results that we obtained during the elaboration of the demonstrators, which were the real use cases that we try to develop here. There were other technological lines that we also considered, like cryptography, and also benchmarking and quantum ops. but we wanted to focus on the demonstrator. We wanted to focus on develop actual use cases and see if quantum computing could provide us with something else that classical solutions provide us today. So we'll start with the first demo. Just a disclaimer, I cannot give a lot of technical information about the first two demos, since I participated on them, but more in a collaborative way. But I worked a lot on the third one, so if you have technical or more specific question about the third one, I will be happy to answer them. So as I was saying, the first demo consisted also in a problem of classification where we tried to use real data, specifically the Eurosat dataset, consisting of satellite images with 10, I think there were 10 different classes. So we have to classify a satellite image and say if this is from the forest or a mountain or many different types of terrain. And we developed 3 different kind of models to test this technology. In the first one, we tried to see if quantum circuits or quantum computing could enhance or make better results in the first layers of CNN architecture. So when we encode the image that we provide to the model, we wanted to see if using quantum circuits could get better results. The second one was kind of the other way around. So we tried to put the quantum circuit at the end of the CNN. Finally, we developed a model which was entirely quantum. So the entire kind of model is represented with a quantum circuit. And for the results we obtained, we were kind of surprised because we didn't expect very good results. As my colleague has told before, we can't expect much nowadays with the quantum computing, but we obtained similar results. We have to also consider that these models are hybrid models. So, for example, in the first 2 models, most of the job, or most of the job is made by a classical neural network. So we give a little bump like at the end with a quantum circuit. But at the end, it was we were happy with the results that we obtained here. Now with the second demonstrator, this was again an optimization problem, but in this case it was coordinated by ITG, and the idea was to optimize the load of 3 batteries in an kind of electrical infrastructure that they have, which is ITG's smart grids, consisting of different batteries and photovoltaic sources of energy, and it was also connected to the national energy system. So we have to optimize the load and deload of these batteries to have the better cost and better energy in the whole systems. We approached this problem using 2 well-known optimization algorithms, QOA, QOA, and BQE, but this last was discarded because due to barren plateaus, and the QOA in this specific case was giving better results in the first tests. And we tested, we see again QMIO in this session. ITG used actually QMIO for the test of this demonstrator. And the results were not as good as the previous demo, but if anyone has been working with quantum optimization, you know, for the many use cases, this is the one that gives you the kind of the worst results for the job, the amount of job that you put into them to formulate the problem correctly, and all the constraints and all the job that is behind this representation of the problem. You don't get the kind of the result that you deserve. But at the end, we were happy to actually represent a big part of the smart grid. So we went further than just simply going to a toy problem with simulated data. We used real data taken from a real smart grid. So we were happy to at least go in that step. So yeah, I don't want to go too much further because we are low on time, but I will explain the last demonstrator, which is one was developed by CTIC, and this was an image generation, so AI generative quantum computing approach. In this case, the idea was to try to generate handwritten images to kind of help or detect fraud in this kind of, in every aspect, in every use of handwritten images. You know, it is used in many different areas like bank accounts, and every interaction that we do, we sign our contract, so it's very interesting. For this case, we use a quantum version of GANs. If you are familiar with this kind of model, they are generative adversarial network models, which consist mainly of two main components, which are the generator and the discriminator. It's called adversarial since the generator and the discriminator are trained simultaneously in parallel in every iteration. They compete for the generator to try to fool the discriminator, and the discriminator try not to be fooled by the generator. So the generator tries to generate images that the discriminator can't discern or know which one is the one generated by the generator or the real image. And this goes with a lot of trouble since these models are very fragile in the sense that you have to make sure that these both components learn at the same time, because if one learns too fast, for example, if the discriminator learns too fast, especially in the initial steps of the training where the generator knows nothing, so it generates random images with noise. If the discriminator learns too fast that this noise is not the real image, then it's going to trivialize, since it's a classificator, it's going to trivialize the reports that goes to the generator, and it's going to tell them all the time that you are doing this wrong, you're doing this wrong, you're doing this wrong, you're doing this wrong, and the generator never learns anything, and then the model collapses, and you've lost your time. Especially, this is bad, especially in quantum computing, since these models, or everything in quantum computing takes a lot of time. So if you spend all that time and your model has learned nothing, is not good. So we made 3 different versions for this model. One using a classical generator, so a neural network, and a quantum circuit, sorry, a neural network for the generator, a quantum circuit for the discriminator. The other way around, so a neural network for the discriminator and a quantum circuit for the generator. And finally, we managed to use a quantum circuit both for the generator and for the discriminator. There were, when we started with this project, there wasn't many literature in this regard in quantum generative AI. So we had to kind of then take some steps, like brave steps, and try new things that no one has tried before. Normally, these kind of models are approached by the different, so we use different generators that each one generates part of the image, and then you compile all of this and you generate the final image. So we wanted to do that, but instead of, for example, generating the first n rows for each generator, we wanted to make it as simple as possible and make each generator have many, many generators, but each one of them generate the smallest non-trivial thing possible, which was a 2 by 2 pixel part of the image. This also provided in a simulation that you can parallelize all of this, since every training is independent, and you can parallelize and gain a lot of save a lot of time. We kind of managed to generate images with dimensions 32 by 128. Since in the literature the images are stacked nowadays in 28 by 28, which is the normally they use the means dataset or the fashion means for the generator, which are stacked in those dimensions. And just to finalize, I present you as some of the results that we obtained for the different models. And the top row is the original image that we kind of pre-processed because the original had a lot of noise, or we want to enhance differences between the background and the actual handwritten part. In the second row, in the first and the third model, I just added the initial state of the model, so the first epoch, and so you know this is all noise. And in the end, after 1,000 and 2,000 iterations, we managed to kind of make something similar to the original image. So we are pretty happy with the results. So yeah, sorry I went too far on time, but thank you, everyone.
Marco, so now we have a talk by Jorge Casco from University of Extremadura, who will present quantum software engineering, a parallelization proposal for quantum computers.
Okay, hello, I'm Jorge from the University of Extremadura. I'm going to explain our proposal for circuit parallelization, which falls under the framework of Test for Efficiency ADH, co-funded by European Union. Okay, I guess almost everyone here have heard about the actual quantum computing as a service architecture. We all have used ABM, and we all know that at first, we develop our circuit, and we send our circuit to the certain service, and our circuit is inside a queue, a task queue, and after hours, minutes, we don't know, our circuit is executed, and we obtain our results. Okay, we and a lot of people in the literature have found several problems in this approach. The first one is high queue times. Now we have queues of minutes and hours, but with the increasing of popularity of quantum computing, this can be even more time. Also, we have seen an underusage of these quantum computers. This is something that in software engineering we do not like. So we have seen that in machines that are up to 100 qubits, people usually use only 10 qubits. And also, we pay for all the machine if we pay to use it. We do not reserve a certain space of qubits. So what do we think with this? Okay, if in classical software we parallelize things to reduce the time spent, etc., why don't we do the same in quantum? Okay, in the top we see the sequential approach, which is the typical one we see, what we use. We have 4 circuits, we launch one after the other. Okay, but what if our quantum computer has enough qubits to support these circuits in parallel? Like, for example, the first 3, which are like 7 qubits, we can launch them in parallel and then the next ones to save time, cost, etc. This will be like the architecture that we developed, in which the developers create their circuits and they send to a certain endpoint, and these circuits go to a quantum task queue using certain algorithms like the ones we developed, like some first in, first out, etc. We select which circuits will go on each composition of circuits, and we send this composition of circuits to the quantum computers. Then we receive the compositions, the combined results, the combined set of results. We decompose this set of results and give the results of each individual circuit to each owner of that circuit. Okay, we have validated this approach already on 4 quantum computers of ABM and AWS, and we have seen very nice results. We have seen that the number of tasks was reduced from like 80 tasks to not even 10 tasks on each computer. And the cost from like $8 for each circuit to less than $1 per circuit. We've tested this with 85 circuits of certain benchmarks like MQT benchmark, etc. And as we see in this table, we have very nice results, like 90% time reduction, 94% of task reduction, and of course reduction, like from almost $800 to 65, for 400 seconds to 17 seconds, which is pretty interesting. So, in conclusion, we find that this proposal is very interesting for researchers. We also help some researchers from University of Castilla-La Mancha. They developed certain framework for quantum circuit testing. They couldn't afford to execute all those circuits, so we helped them with this proposal, and we are publishing a paper with them. And that's it. We think that this is an important proposal for quantum circuits or quantum software engineering because of the nice validation we are getting. What are we expecting, or what do we want from this? We are asking for 2 windows of time in which we want to execute the circuits on parallel and circuits on sequential, because we want to test if the sequential approach is most energy efficient than the parallel approach is more energy efficient than the sequential approach. We think it is, but we haven't tested, so we're asking for certain elements of like consumption, average consumption, etc., whatever we can obtain to test if we are right and to check if parallelization is even better than we have thought. So that's it. Thank you for your attention.
Thank you very much, Jorge. So now we have time for a few questions, since it's the end of the whole session.
Thank you for all the talks, are very interesting. Question for two?
It depends if it's more technical.
No, you were talking about this number, that it was important, but also at your first part you were talking about that you obtain outliers in your.
We don't obtain outliers. We classify better the outliers.
The outliers.
The outliers. Okay. Because sometimes with the classical, what we have seen is that these outliers are not well classified. Mm-hmm. So we expected that these outliers would be better classified. For example, I put an example. There are people that love cheap things, or that seems that they love cheap things, because they love a coffee. But then they add, I love a coffee in New York. This will be how we classify in classical marketing this, because it's a opposite, because love coffee. But in New York, these outliers in O1 will be classified in like coffee, cheap, not caviar. But with quantum, we expect, when we could rise to big data, of course, this is a test, but we expect to have this kind of information. We need to work, we need that the technology will be more mature, we need lots of things. But we expect, because the problem, it's not classical, because the problem, in this case, it's not, it's a superposition, no? It's from more, I don't know if I have answered.
But
Yeah?
Because in my mind, when I didn't hear well your words, but in my mind I was thinking on, okay, quantum computer nowadays is an open system. It's physically defined as an open system. That means that it interacts with the environment, the qubits with the covariance and so on. I was thinking that maybe it's helpful for them, for the training, that appears new data because of the noise and that. But yeah, but maybe, I don't know, you can answer that part, I think.
Well, I'm not sure. I think this was just a pilot, so we are not at the point in which we can actually tell something more concrete, no? So I think at this point it's just to, as we were talking before, no, just to put the things setting up and start working with something. But currently we're not sure yet.
Okay. Thank you. Well.
Is there any other? Yeah, I guess.
Jorge, what about the quality of the results you are receiving back? Is it good enough in the sequential, well, in the parallel against the sequential approach?
Well, we have seen that we are losing some quality on the results, like 20% more or less. But we are trying to decrease it. We are now on one line of our research, which is putting those circuits on the qubits that has less noise to greatly reduce that number of decrease of quality of the results. Now we're like 20–30% increasing of noise, but we're trying with different forms trying to reduce it.
Okay, thank you.
Thank you. Just a question: how you post-process the information? Because when you're dealing with estimate the results, but with an operator, say, how do you separate the bit string from the operator? And how?
We used quantum circuits of the benchmark, and we pick the counts of each.
So you're sampling then?
Yeah.
And then you operate the thing. Okay. Thank you. But in that sense, how you just separate like the first three correspond to this problem, but you never made an optimization of the parameters and so on.
No,
you're just sampling.
we have not reached that step yet.
Because I thought about your idea once, but I said like maybe it's tricky.
Okay.
Yeah, but thank you.
I am very sorry, but I have to close the session because we are late and the people are working there and maybe they want to leave. So thank you very much for all the speakers of this session. Thank you very much for all the speakers that we had today. We have some new requirements that I collected during your presentation. Not all of them I have here because we will read all the presentations again and we can analyze, but in any case, if you want to communicate us any new requirement, please don't hesitate to contact Irais or Raúl at BSC, sorry, and because we want to help you. But to summarize the requirements apart the nice presentations. First of all, create a community, and create a community. We will do that, okay, soon, because it's something that we are doing in other areas. So in this case, I think that is a good idea because the support is more complex than in another that we have history Okay. More computes, yes, of course, but with high quality, because it's important as well. Okay, and more QPUs, because we need to run in parallel some of the much time for programming, I cannot solve your problem. But clearly, the other round is to have higher APIs. That is the other requirement that we have, not working at the low level, try to increase the level of programming of the systems. Okay, emulators in ONA, in BSC with GPUs. Okay, at CESGA you know that you have emulators, even with GPUs, because in Finisterrae-3 we have some of the emulators installed there, and you can use GPUs. But the problem is that the GPUs are very expensive, not in money, in time waiting for achieving, just getting one GPU. Okay, the demand is incredibly high at this moment. Having a Hamiltonian model, an initial Hamiltonian model for the qubits, this is really very expensive, complex, and we would try to do, but it's really a heavy demand. Okay. Increase the execution time. I think that this is mainly for ONA, because in our case it's 2 hours maximum per job, and we have now the problem of 30 seconds of initialize. It's only 0.5 seconds, but we take note of that as well. In ONA, they asked to reduce the initialization time for executing a circuit. I didn't know that problem. We have to work together to solve this issue. Okay. We need parallelization. The last talk is clear. Okay, but there are other, in chemistry, for example, they are demanding parallelization. For the reason we developed QUNQA, because QUNQA is designed to make parallelization in the future, but now in emulators. That is missing. We are trying to mix the QPUs with the emulators at the same time, in the same job. Okay, but it's not ready yet. Energy consumption and other units, like the consumption of water, of the production of CO2. This is a research project around the world at this moment. So I cannot promise you that we can provide this information, because in fact there is one very nice international project that is Quantum Energy Initiative, in order to understand the consumption of the quantum computers, and if really they can provide advantage as well in energy consumption. But we are working on. I know that you have requested more things, but this is the main summary of this workshop. Thank you for your input, and I hope to organize next year another workshop, and you will be here as well. Thank you.